Tonight, we're exploring the terrifying truth about quantum entanglement, a discovery so strange that it made Albert Einstein question the very foundations of reality. Imagine two tiny particles becoming linked in such a profound way that no matter how far apart they drift, even across opposite sides of the universe, measuring one seems to instantly influence the other. It sounds impossible. It sounds like science fiction. And yet, after decades of experiments, this is exactly what nature appears to do. If you enjoy these slow journeys through the mysteries of space, physics, and the universe, I'd really appreciate it if you took a moment to like the video and subscribe. And before we begin, let me know in the comments where you're listening from, and what time it is where you are. It's always fascinating to see people from all over the world sharing these quiet moments together. Now, there's nothing else you need to do tonight. If you haven't already, dim the lights a little. Let your shoulders relax. Sink a little deeper into your pillow, your chair, or wherever you've decided to spend the next little while. You don't need to remember every detail that follows. You don't need to solve quantum physics before you fall asleep. If your thoughts drift away for a while, that's perfectly fine. My voice will simply continue, gently guiding you through one of the strangest stories science has ever uncovered. Because tonight isn't just about tiny particles. It's about the possibility that everything you've ever believed about distance, connection, and even reality itself may only be part of a much deeper picture. Over the next 2 hours, you'll travel from the earliest arguments between the greatest physicists in history to experiments that seemed impossible, to discoveries that continue to puzzle scientists today. Along the way, you'll quietly step inside a universe where two particles can remain connected across unimaginable distances, where information behaves in ways that seem to defy common sense, and where some physicists have begun to wonder whether space itself might emerge from hidden quantum relationships. The deeper you travel, the stranger the universe becomes. And perhaps the most unsettling realization isn't that quantum entanglement exists. It's that nature has been quietly doing this all along, whether anyone was watching or not. So take one slow breath. Let the outside world grow a little quieter. And together, let's begin with a simple question that changed physics forever. How could two particles remain connected, even after the universe itself has pulled them unimaginably far apart? Imagine holding something so small that no human eye could ever hope to see it. Not a grain of dust. Not a single cell. Something unimaginably smaller. A tiny particle, one of the countless building blocks that quietly make up everything around you. Your body. The air in your room. The pillow beneath your head. Even the faint glow of distant stars began as collections of particles like these. Now imagine creating two of them together. For just the briefest moment, they share the same tiny corner of the universe. Their existence begins as one small event, almost like two ripples spreading across the surface of a perfectly still lake. Then very slowly they drift apart. At first they're separated by only a few centimeters, then a few meters, then a few kilometers. Perhaps one leaves Earth entirely, carried aboard a spacecraft sailing silently beyond the moon. Years pass. Decades. Eventually one particle circles a distant star while the other remains here, resting quietly inside a laboratory on Earth. By now, the distance between them has become almost impossible to picture. Light itself, the fastest thing the universe allows, would need years to travel from one particle to the other. If you were standing beside the particle on Earth, shining the brightest flashlight ever built into the darkness, its beam would still be racing through empty space long after your own lifetime had ended. Surely by then the two particles would have become complete strangers. After all, that's how the world around you works. When two friends say goodbye at an airport, they stop sharing experiences. One may wake beneath a rainy sky while the other watches the sunrise somewhere across an ocean. The farther apart they become, the less connected their lives feel. Distance separates things. It's one of the oldest intuitions you have. You feel it every day without thinking about it. If someone whispers beside you, you hear them instantly. If they whisper from another room, the sound arrives a moment later. If someone shouts from the other side of the world, you won't hear them at all unless technology carries their voice across the distance. Everything seems to obey this quiet rule. Nothing influences something else without a journey in between. Even sunlight takes over 8 minutes to reach Earth. The glow warming your face on a summer afternoon actually began its journey while you were still making breakfast. The universe, it seems, has a built-in speed limit. Messages travel. Light travels. Gravity travels. Everything waits its turn. Now imagine breaking that rule. Not bending it, not stretching it, ignoring it completely. Imagine that, here on Earth, you gently examine one of those tiny particles. The very instant you do, something remarkable appears to happen. Far away, So far away that even light has barely begun its journey, the second particle somehow seems to respond. No visible signal crosses the emptiness. No flash of light. No invisible wire. No hidden radio transmission. Nothing that anyone can detect. Yet somehow the distant particle behaves as though it already knew what had happened. If you've never encountered this idea before, your first reaction is probably the correct one. That can't be right. It sounds less like physics and more like magic. Perhaps there is a hidden connection stretching between them. Perhaps there's information moving faster than light. Or perhaps scientists have simply misunderstood what they're seeing. Those possibilities all sound far more comfortable than accepting that nature itself behaves this way. And for a long time, many brilliant people believed exactly that. Because if this strange connection were real, it wouldn't simply change one small corner of physics. It would force you to rethink something much deeper. It would challenge the idea that objects possess completely separate existences once they move apart. Take a moment to picture the night sky above you. On a clear evening, thousands of stars seem scattered randomly across the darkness. Each one appears independent, separate, alone. Yet what if the universe isn't quite as divided as it looks? What if separation is, in some subtle way, an illusion born from the limitations of everyday experience? The thought feels almost unsettling. Your entire life has been built upon the assumption that things here cannot instantly affect things unimaginably far away. You trust that assumption every time you send a message, watch the moon rise, or look toward distant galaxies whose light has traveled millions of years just to reach your eyes. Without realizing it, you've always believed that distance protects independence. Physics once believed that too. In fact, for centuries, this principle seemed so obvious that nobody questioned it. Isaac Newton described gravity with astonishing precision, but even his equations left later scientists wondering how gravity actually reached across empty space. Eventually, Albert Einstein provided a deeper answer through his theory of relativity, showing that even gravity does not act instantaneously. Changes spread through the fabric of spacetime at the speed of light. It was a beautiful picture. Elegant, orderly, comforting. Nothing could outrun light. Nothing could leap instantly across the universe. Reality itself appeared to respect boundaries. Then, during the 20th century, physicists began performing experiments on the smallest scales imaginable. Again and again, nature whispered the same impossible message. The microscopic world refused to behave like the familiar one. Particles didn't always seem to possess definite properties before they were measured. Chance appeared woven into reality itself. And occasionally, two particles behaved with a kind of mysterious coordination that no existing theory could comfortably explain. At first, many scientists assumed the experiments must be flawed. Perhaps the instruments weren't precise enough. Perhaps there were hidden variables no one had yet discovered. Perhaps the strange results would disappear as measurements improved. Instead, the opposite happened. Every new experiment made the mystery even harder to ignore. It was as though the universe had quietly hidden one of its greatest secrets beneath the surface of ordinary experience, waiting for curious minds to stumble upon it. Tonight, you're following those same footsteps. Not toward a frightening discovery, but toward one that gently asks you to loosen your grip on intuition. Because over the next few moments, you'll encounter an idea that seems so absurd that one of history's greatest physicists spent years trying to prove it wrong. And yet, the universe never changed its answer. It simply continued behaving in the same strange, quiet way it always had. Before anyone gave this phenomenon a name. Before anyone argued over what it meant. Before scientists built experiments to test it. There was only one simple, unsettling question. How could two tiny particles, separated by unimaginable distances, continue to behave as though they had never truly parted at all? If you had walked into a physics laboratory a little more than a century ago and described the strange connection you've just imagined, most scientists would probably have smiled politely before explaining why such a thing simply couldn't happen. The universe, they would have said, is built upon causes and effects. Something happens. A signal travels. Something else responds. Even if the process is unimaginably fast, there is always a chain connecting one event to the next. It is an idea so deeply woven into everyday experience that you rarely notice it. When you press a light switch, electricity races through the wires before the room fills with light. When thunder follows lightning, the sound arrives later because it moves more slowly through the air. Everything waits for something. Nothing simply knows. And yet, as physicists began exploring the quantum world, nature repeatedly refused to follow these comfortable expectations. Imagine returning to those two tiny particles. They began their existence together, almost like two dancers learning the same rhythm before stepping onto separate stages. While they remain together, physicists describe them with a single shared quantum state. It is not that one particle secretly carries half the information while the other carries the rest. Instead, the pair behaves as though it forms one complete system, even after the particles drift apart. This shared condition is what scientists call quantum entanglement. The name itself sounds mysterious, but the idea is surprisingly simple to describe, even if its consequences are anything but simple. Two particles become linked in such a way that certain properties of one are perfectly related to the properties of the other. Suppose you measure one particle and discover that it has one possible state. Instantly, you know what result you will obtain when measuring its partner, no matter how far away that partner may be. At first glance, this doesn't sound especially remarkable. After all, imagine placing a left-hand glove in one box and a right-hand glove in another. You send one box to New York and the other to Tokyo. The moment you open the first box and find the left glove, you immediately know the second box contains the right one. Nothing mysterious happened. The gloves already had their identities before you looked. For a while, many physicists hoped entangled particles behaved the same way. Perhaps each particle carried hidden instructions from the moment they separated. Maybe the universe only appeared mysterious because those instructions were invisible to us. It was an appealing explanation. Comforting even, but there was a problem. Real quantum experiments didn't behave like hidden gloves. Again and again, researchers discovered correlations that were stronger, stranger, and more precise than hidden instructions seemed capable of producing. It was as though the particles weren't merely revealing information they had always possessed. Instead, the relationship itself appeared fundamental. If that sounds difficult to picture, you're in good company. Some of the greatest scientific minds who ever lived struggled with exactly the same feeling. One of them was Albert Einstein. By the time quantum mechanics emerged, Einstein had already transformed humanity's understanding of space, time, gravity, and light. Few people understood the universe more deeply than he did. Yet when confronted with entanglement, he found himself deeply uncomfortable. Not because the mathematics was poorly constructed. Not because the experiments lacked precision. But because the implications seemed almost impossible to accept. If entanglement were truly real, then reality itself appeared to violate one of its oldest principles, that distant objects should possess their own independent existence unless something physically connects them. Einstein famously referred to the phenomenon as spooky action at a distance. The phrase has become legendary, but it wasn't intended as praise. It was criticism. To Einstein, the idea felt incomplete. He believed that somewhere beneath quantum mechanics there must be a deeper layer of reality, a hidden set of rules that restored common sense to the universe. Surely, he thought, nature could not be this strange. It is easy to sympathize with him. Even now, sitting comfortably in your own room, the idea probably resists intuition. Imagine standing beneath a sky filled with stars. Some of those stars are hundreds of light years away. Others are thousands. The most distant galaxies visible through powerful telescopes are so unimaginably far that their light began traveling toward Earth before human civilization even existed. The universe feels vast precisely because distance matters. It takes time to cross. It creates separation. It limits communication. And yet, entanglement quietly suggests that on the deepest level of reality, separation may not be quite what it appears to be. Notice that this does not mean information is magically racing faster than light. It does not mean invisible messages are flashing across the cosmos every time a particle is measured. In fact, as you'll discover later, Einstein's speed limit remains perfectly intact. That is part of what makes entanglement so endlessly fascinating. Nothing obvious is being transmitted. No known law of physics is openly broken. And still, the universe behaves in a way that seems to challenge your intuition at every turn. The more carefully scientists examine these strange quantum relationships, the less they resembled a clever illusion and the more they resembled a genuine feature of reality itself. It was as though the universe was quietly whispering that your everyday picture of space and separation was only an approximation. A useful story that works beautifully for planets, people, and stars, but begins to unravel among the smallest building blocks of existence. For decades, the debate continued. Was quantum mechanics incomplete? Were hidden variables waiting to be discovered? Or was nature truly as strange as it appeared? One physicist would eventually realize there was a way to settle the argument, not with philosophy but with an experiment. It was an idea so elegant that it transformed one of science's greatest debates into a question the universe itself could answer. And when that answer finally arrived, it would change physics forever. Imagine, for a moment, that you've traveled back to the early years of the 20th century. The world feels both familiar and completely different. Steam trains still cross vast landscapes. Cities glow beneath rows of electric lights that seem wonderfully modern. Radios are beginning to connect voices across great distances. Airplanes are little more than fragile machines made of wood and fabric. Humanity has only just begun to believe that science can explain almost everything. And standing quietly at the center of this scientific revolution is a man with untidy hair and thoughtful eyes. Albert Einstein. By this point, he has already changed the way humanity understands the universe. Space is no longer an empty stage where events simply happen. Time is no longer a universal clock ticking the same for everyone. Together they form a single fabric, spacetime, that bends, stretches, and curves beneath the presence of matter and energy. It is one of the most beautiful ideas ever discovered. And perhaps even more remarkable, nature agrees with it. Light bends around stars exactly as Einstein predicted. Clocks run at different speeds depending on gravity and motion. Even the GPS satellites quietly helping people navigate Earth each day must account for Einstein's equations in order to remain accurate. Again and again, the universe confirmed his extraordinary intuition. It would have been easy to believe that the deepest mysteries of reality were finally falling into place. But while Einstein was refining his elegant picture of the cosmos, something strange was happening elsewhere. Far from galaxies and black holes, physicists were turning their attention inward, exploring a realm so unimaginably small that ordinary experience offered almost no guidance. The world of atoms. Then electrons. Then particles even smaller still. The deeper they looked, the stranger everything became. Imagine shrinking yourself until an entire atom becomes as large as a cathedral. You drift silently through what appears at first to be almost complete emptiness. The nucleus sits at the center like a tiny glowing ember, while electrons refuse to behave like tiny planets orbiting around it. Instead, they seem more like hazy possibilities spread throughout space in ways that defy ordinary intuition. Nothing here feels solid. Nothing behaves predictably. It is as though certainty itself has begun to dissolve. For centuries, physics had operated according to a wonderfully reassuring principle. If you know everything about a system, its position, its speed, the forces acting upon it, you should, in principle, be able to predict exactly what will happen next. The universe behaved like an unimaginably complex clock. Every gear influenced another. Every cause produced an effect. Every event followed naturally from the one before it. The future was simply waiting to unfold. Quantum mechanics challenged that comforting picture. Instead of certainty, it offered probabilities. Instead of precise paths, it described clouds of possibility. Instead of knowing exactly where a particle would be, physicists could often only calculate where it was most likely to appear when measured. To many scientists, this wasn't simply surprising. It felt incomplete. Einstein shared that feeling more strongly than almost anyone. He wasn't rejecting mathematics. In fact, he admired much of quantum theory. Its equations worked astonishingly well. Again and again, experiments confirmed its predictions with extraordinary accuracy. The problem wasn't whether quantum mechanics was useful. The problem was what it seemed to say about reality. Imagine tossing a coin into the air. Even if you can't predict whether it lands on heads or tails, you naturally assume the answer already exists before you look. The coin isn't somehow both heads and tails at the same time. Your uncertainty belongs to you, not to the coin. Einstein believed the universe worked in much the same way. If a particle seemed unpredictable, perhaps that simply meant scientists hadn't yet discovered all the hidden information controlling its behavior. After all, ignorance is not the same as randomness. If you don't know where every molecule inside a hurricane is moving, the storm appears unpredictable. That doesn't mean the hurricane has abandoned the laws of physics. It simply means the calculation is too complicated. Einstein suspected quantum mechanics suffered from a similar limitation. Perhaps there were deeper rules operating beneath the surface. Invisible variables. Unknown causes. A hidden layer of reality waiting to be uncovered. Many physicists quietly agreed. It seemed far more reasonable than believing nature itself behaved randomly. After all, randomness feels uncomfortable. You instinctively search for causes. If a glass falls from a table, you look for the hand that knocked it over. If the lights suddenly go out, you assume something happened at the power station. Everyday life trains you to expect explanations. The universe, you feel, should always have reasons. Quantum mechanics appeared to disagree. It suggested that, at the smallest scales, some events simply cannot be predicted with absolute certainty, not because the theory is incomplete, but because certainty itself may not exist in the way you imagine. It was a profoundly unsettling idea, not just scientifically, philosophically. It challenged humanity's oldest assumptions about cause and effect, knowledge and reality itself. Einstein famously expressed his discomfort with a sentence that has echoed through physics ever since. God does not play dice with the universe. Whether or not you share Einstein's beliefs, the deeper meaning is clear. He could not accept that the universe was fundamentally governed by chance. He believed there had to be something more. Some deeper order. Some hidden architecture beneath the strange mathematics. For years, this disagreement remained largely philosophical. Brilliant minds debated late into the night, filling chalkboards with equations and lecture halls with arguments. But no amount of discussion could determine who was right. To settle the question, someone would eventually need to find a way to test reality itself. And hidden within Einstein's own objections was the clue that would make such a test possible. Imagine sitting quietly in Einstein's office during the mid-1930s. The room is peaceful. Sheets of paper are scattered across a large wooden desk. Equations fill notebooks that have been opened and reopened countless times. Outside the window, the world continues its ordinary rhythm. People walk through the streets, trains arrive on schedule, and the stars will soon appear overhead, following paths that have inspired wonder for thousands of years. Yet inside this quiet room, Einstein is wrestling with a question that refuses to leave him alone. He is not trying to destroy quantum mechanics. Quite the opposite. He knows better than almost anyone that its predictions are astonishingly accurate. Every year, more experiments confirm that the mathematical framework works beautifully. It describes atoms, light, and countless microscopic phenomena with remarkable precision. But Einstein believes that a successful theory should do more than make correct predictions. It should also describe reality itself. There is an important difference between those two ideas. Imagine watching a weather forecast. It tells you there is an 80% chance of rain tomorrow. The prediction may turn out to be correct, but you still understand that something physical is happening in the atmosphere. Winds are moving. Clouds are forming. Tiny droplets of water are gathering high above your head. The forecast reflects your knowledge of the weather, not the weather's uncertainty about itself. Einstein believed quantum mechanics should work in the same way. Its probabilities, he suspected, reflected missing knowledge rather than fundamental randomness. Somewhere beneath the equations, hidden from view, reality should already possess definite answers. If only scientists could uncover those deeper rules, the apparent mystery would disappear. To challenge quantum theory, Einstein joined two fellow physicists, Boris Podolsky and Nathan Rosen. Together, they published a paper that has become one of the most famous in the history of physics. Today it is known simply as the EPR paper, named after the first letter of each scientist's surname. Rather than trying to prove quantum mechanics wrong through new experiments, they chose a different approach. They asked a question. A wonderfully simple question. Suppose two particles interact for a short time before moving far apart. According to quantum mechanics, the particles remain connected in a very unusual way. If you measure one particle, you instantly know something about the other. How could that be possible? Einstein saw only two reasonable explanations. The first possibility was that each particle already carried complete information from the moment they separated. Their properties were fixed all along, even if no one knew what those properties were. The second possibility was much stranger. Perhaps measuring one particle somehow influenced the other instantly, regardless of distance. Einstein found that second option unacceptable. Not because he disliked strange ideas. His own theories had already overturned centuries of conventional thinking. But because this possibility appeared to violate one of the deepest principles in all of physics. Locality. Locality is an elegant idea. It simply means that objects are directly influenced only by their immediate surroundings. For something happening here to affect something over there, some influence must travel between them. Perhaps it travels as light. Perhaps as a gravitational wave. Perhaps in another form entirely. But it must make the journey. Nothing should simply leap across empty space without crossing it. This principle fits beautifully with your everyday experience. If someone lights a candle across the room, the light takes a tiny fraction of a second to reach your eyes. The delay is so small you never notice it, but it exists. Even sunlight, despite racing through space at nearly 300,000 kilometers every second, still needs more than 8 minutes to travel from the sun to Earth. The universe, it seems, respects distance. And because it respects distance, it also respects time. This is one of the foundations of Einstein's theory of relativity. No usable information can travel faster than light. It is not merely a speed limit. It is woven into the structure of spacetime itself. So when quantum mechanics appeared to suggest that two distant particles remained mysteriously connected, Einstein concluded that the theory must be incomplete. There had to be hidden variables, unknown pieces of information carried by each particle from the beginning. These hidden variables would determine every future measurement while preserving locality. In other words, the universe could remain sensible after all. For many years, this seemed like an entirely reasonable position. In fact, if you had been alive during those debates, you might well have agreed with Einstein. His explanation required no magic, no impossible signals, no mysterious influences crossing the universe, only the assumption that reality contained more information than physicists had yet discovered. The debate settled into an uneasy balance. Quantum physicists pointed to equations that worked perfectly. Einstein pointed to a philosophical problem that refused to disappear. Neither side could decisively defeat the other. The disagreement became one of the greatest scientific mysteries of the 20th century. Was quantum mechanics a complete description of nature? Or was it only the visible surface of something deeper? For decades, there seemed to be no way to find out. The hidden variables, if they existed, remained hidden. The strange quantum predictions, meanwhile, continued matching experiment after experiment. It was almost as though the universe was smiling quietly while humanity argued over how it really worked. Then, in the 1960s, a quiet physicist from Northern Ireland looked at Einstein's challenge from an entirely different perspective. Instead of asking who was right, he asked a more powerful question. What if reality itself could decide? What if there were an experiment capable of distinguishing Einstein's hidden universe from the strange quantum universe described by the equations? It was an idea so elegant that it transformed decades of philosophical debate into something wonderfully simple. A test. One that nature could answer for itself. And when physicists finally performed that test, the result would become one of the most astonishing discoveries in the history of science. Imagine arriving at a point where one of the greatest scientific debates in history has reached a standstill. For decades, two competing pictures of reality have quietly existed side by side. On one side stands Albert Einstein, convinced that the universe must possess a deeper order than quantum mechanics can describe. Somewhere beneath the strange probabilities and mysterious measurements, hidden variables are quietly guiding every particle, preserving the elegant logic that has always defined physics. On the other side stands quantum mechanics itself. Its equations continue predicting experimental results with astonishing accuracy, yet they seem to paint a universe that is fundamentally stranger than anyone had imagined. A universe where certainty gives way to probability, and where distant particles appear connected in ways that challenge ordinary intuition. Neither side has been able to convince the other. It is as though two maps describe the same landscape, yet each insists that the other has overlooked something essential. For years, physicists debated these ideas in lecture halls, universities, and quiet offices much like Einstein's. Chalkboards filled with equations. Conferences ended with thoughtful disagreements rather than clear conclusions. Every new discussion seemed to circle back to the same unanswered question. How could anyone ever know which picture of reality was true? After all, hidden variables were, by definition, hidden. If they existed, they lay beneath the surface of every experiment. If they did not exist, then quantum mechanics would stand alone as the deepest description of nature ever discovered. The problem seemed impossible. How do you test something that cannot be seen? Imagine trying to determine whether a sealed clock contains invisible gears without ever opening the case. You could listen carefully. You could watch the hands move. You could compare it to other clocks. But unless something about its behavior revealed the hidden machinery inside, the mystery would remain forever. Physics appeared trapped in exactly this situation. Or so everyone believed. Then, in the early 1960s, a young physicist named John Bell began looking at Einstein's argument from a completely different angle. Bell was not interested in defending one side simply because it seemed more intuitive. Nor was he satisfied with accepting quantum mechanics merely because it worked. He wanted something far more valuable. He wanted reality itself to settle the debate. Imagine sitting quietly with Bell as he studies the problem. Unlike Einstein, Bell is not asking whether hidden variables might exist. Instead, he asks a much more subtle question. If hidden variables really do exist, what observable consequences would they have? In other words, could a universe governed by Einstein's hidden rules ever be distinguished from a universe governed entirely by quantum mechanics? At first glance, the answer seems obvious. Probably not. If hidden variables are hidden, surely they remain hidden forever. But Bell realizes something extraordinary. Even invisible rules leave fingerprints. Imagine watching two dancers perform on separate stages miles apart. If they were following completely independent choreography, their movements would occasionally match by coincidence. If they had memorized the same routine beforehand, their movements would agree much more often. And if, somehow, they remained perfectly synchronized no matter how unpredictably the music changed, you would immediately suspect that something far stranger was happening. Bell realized that hidden variable theories and quantum mechanics predicted different kinds of correlations. Not dramatically different. Not differences you could notice by watching a single pair of particles. But differences that would slowly emerge after measuring thousands, then millions, of entangled pairs. The distinction was incredibly subtle. Like listening to two orchestras perform the same symphony and noticing that, every so often, one violin arrives a fraction of a heartbeat earlier than expected. Most listeners would never hear the difference. But careful measurement would. Bell transformed Einstein's philosophical objection into mathematics. He derived a remarkable relationship, today known as Bell's inequality. Despite its intimidating name, the underlying idea is beautifully simple. If Einstein's hidden variable picture is correct, then there is a strict limit to how strongly distant particles can be correlated. Nature simply cannot exceed that limit. No matter how cleverly the hidden variables are arranged, no matter how complicated the unseen machinery becomes, the particles can only agree with each other up to a certain point. Quantum mechanics, however, predicts something astonishingly different. According to its equations, entangled particles should sometimes exceed Bell's limit. Not by accident. Not because of experimental error. But because reality itself behaves differently than Einstein imagined. Suddenly, the impossible had become testable. For the first time, physicists possessed something neither side had ever had before. A prediction. Two competing descriptions of reality now expected different experimental outcomes. The universe could no longer hide behind philosophy. Would have to choose. Imagine how exciting, and perhaps unsettling, that realization must have been. For decades, scientists had argued about the foundations of reality using logic, intuition, and mathematics. Now the debate was leaving the chalkboard. The answer would come from nature itself. But designing such an experiment was anything but easy. The particles involved were unimaginably small. Their quantum states were extraordinarily delicate. The slightest disturbance from the surrounding environment could destroy the very effects researchers hoped to observe. It was like trying to hear the faintest whisper during the middle of a hurricane. The technology simply wasn't ready. Years passed. Experimental techniques improved. Lasers became more precise. Detectors became more sensitive. Researchers around the world slowly assembled the tools needed to ask one of the most profound questions humanity had ever posed. Was Einstein right? Or had the universe been stranger than even he could imagine all along? Eventually, in the early 1980s, a team led by the French physicist Alain Aspect prepared to perform one of the most famous experiments in modern science. Every mirror had to be aligned with extraordinary precision. Every detector calibrated. Every possible source of error considered. Because whatever happened next would not merely test a theory. It would test one of the deepest assumptions humanity had ever made about reality itself. And when the measurements finally began, the universe gave an answer that almost nobody expected to be so clear. Imagine standing inside the laboratory as everything finally falls silent. The equipment has been calibrated countless times. Mirrors reflect faint beams of laser light across the room. Sensitive detectors wait patiently, ready to capture events so small and so brief that they unfold billions of times every second without anyone ever noticing. For years, physicists had prepared for this moment. Not because they expected to discover a new particle or a hidden force, but because they were about to ask the universe a simple question. Are you the kind of universe Einstein imagined? Or are you even stranger? The experiment itself was surprisingly elegant. Pairs of entangled photons were created together before traveling in opposite directions towards separate detectors. As each photon arrived, scientists measured one of its properties using detectors whose settings could be changed while the photons were already in flight. That detail mattered enormously. If Einstein's hidden variables were real, the photons would have needed to know in advance which measurements they would face. By changing the detectors quickly and unpredictably, researchers made that explanation increasingly difficult. One pair of photons revealed almost nothing, nor did 100. Even 1,000 measurements could still be dismissed as coincidence. But as the data slowly accumulated, a pattern began to emerge. It was subtle at first, hidden beneath columns of numbers. Then it became unmistakable. Again and again, the correlations between the entangled particles exceeded the limit that John Bell had calculated decades earlier. Bell's inequality had been violated. It is difficult to overstate what that meant. Remember the dancers from earlier. If they had simply memorized the same routine before stepping onto separate stages, there would always be limits to how perfectly their performances could match. Bell had calculated those limits. Yet nature kept dancing in a way that surpassed them. Whatever was happening, it could not be explained by ordinary hidden instructions prepared in advance. For many physicists, it was one of those rare moments when reality turned out to be even more surprising than imagination. Einstein's preferred explanation, the comforting idea that particles secretly carried complete information all along, could no longer explain the experimental results. The universe had quietly rejected it. That does not mean Einstein was a poor physicist. Far from it. His objections forced quantum theory to become stronger. Without his relentless questioning, Bell might never have discovered a way to test the foundations of quantum mechanics at all. In a sense, Einstein helped create the very experiment that challenged his own intuition. Science often advances this way. The greatest discoveries are not born from everyone agreeing. They emerge because brilliant people ask difficult questions and refuse to accept easy answers. As the years passed, Aspect's experiment was repeated again and again. Different laboratories, different technologies, different researchers. The distances between entangled particles grew larger. The measurements became faster. The detectors became dramatically more accurate. Each new generation of experiments closed another possible loophole. Could the particles somehow have exchanged an unnoticed signal? Researchers designed experiments to prevent that. Could hidden flaws in the detectors explain the results? New experiments ruled that out as well. Eventually, entangled particles were tested across rivers, across mountains, between islands, and even between Earth and orbiting satellites. One remarkable experiment sent entangled photons over more than 1,000 kilometers through space, confirming that the same strange correlations persisted over distances that would have seemed unimaginable only a few decades earlier. No matter where scientists looked, nature gave the same quiet answer. The quantum connection remained. And yet, something equally remarkable became clear. Despite how strange entanglement appeared, it never allowed people to send messages faster than light. This is one of the most common misunderstandings about quantum mechanics. If two particles remain mysteriously connected, why not use them as an instant communication device? Why not send messages across the galaxy in an instant? The answer is surprisingly subtle. Although the measurement outcomes are correlated, each individual result still appears completely random. You cannot choose the outcome of your own measurement, which means you cannot encode a message into it. Only later, when observers compare their results using ordinary communication that still travels no faster than light, does the extraordinary pattern emerge. Einstein's cosmic speed limit survives. Relativity survives. And yet the mystery survives with it. That may be the most fascinating part of all. Physics did not replace one simple picture with another. Instead, it revealed that two ideas which seem impossible to reconcile can both be true. Nothing travels faster than light. And somehow, entangled particles exhibit correlations that no local hidden variable theory can explain. If that feels difficult to picture, don't worry. Some of the world's greatest physicists feel exactly the same way. Even today, nearly a century after Einstein first objected to quantum mechanics, researchers continue debating what these experiments truly mean. The mathematics is no longer in doubt. The observations are no longer in doubt. What remains uncertain is something even deeper. What kind of reality produces these extraordinary results? Perhaps the particles are not communicating at all. Perhaps our ordinary understanding of separation is incomplete. Or perhaps the fabric of reality itself is woven together in ways that our everyday intuition was never meant to perceive. As you continue this journey, the questions become even more profound. Because once you accept that entanglement is real, another mystery quietly takes its place. How can two particles remain connected across unimaginable distances, if nothing is actually traveling between them? Imagine floating in complete darkness. Not the darkness of a room after you've turned off the lights. Not even the darkness between the stars. This is the quiet darkness of intergalactic space, where entire galaxies have become faint islands of light scattered across an ocean so immense that your mind almost refuses to picture it. There is no sound here. No wind. No up or down. Only silence. Ahead of you, suspended against the blackness, are two tiny particles. At first they rest side by side, born together in the same brief quantum event. If you could somehow see them, and in reality they are far too small for any eye, they would appear perfectly ordinary. Nothing about them hints at the extraordinary story they are about to tell. Then they begin to drift apart. Slowly at first. Almost gently. One moves to your left. The other to your right. The distance between them grows with quiet patience. A few meters become a few kilometers. A few kilometers become the distance between cities, then continents. Soon one particle remains somewhere near Earth while the other continues outward, passing the moon before disappearing into the vast darkness beyond. You continue watching. Years seem to pass effortlessly. The particle races beyond the planets, leaving the familiar warmth of the sun behind. It slips past the icy worlds at the edge of the solar system before entering the enormous emptiness between the stars. If you could look back, the sun would now appear as nothing more than another bright point among countless others. Still, the particles continue separating. One remains unimaginably far away. The other remains where it began. Between them lies a gulf so enormous that even light, the fastest traveler the universe allows, would need years to make the journey. And yet physicists tell you that these two particles remain connected. Not by a wire. Not by a beam of invisible energy. Not by some hidden thread stretching through the darkness. Simply, connected. It is a sentence that almost invites misunderstanding. When you hear the word connected, your imagination naturally reaches for familiar images. You picture ropes, bridges, telephone lines, internet cables crossing the ocean floor. Even wireless communication still relies on radio waves quietly spreading through space. Everything you know about connection involves something moving from one place to another. Nature has trained you to think this way. If two friends speak across a video call, millions of tiny signals race through fiber optic cables and satellites before their voices reach each other. If you switch on a lamp, electricity flows through metal wires hidden inside your walls. If gravity pulls the Earth around the sun, even that influence travels through spacetime at the speed of light. Connection in everyday life always seems to require a journey. Entanglement refuses to fit that picture. This is why so many people first encountering the idea imagine that physicists have discovered some kind of invisible communication. It is an understandable conclusion, but it is not what the experiments reveal. Imagine standing beside one of the particles. You decide to observe it. Nothing dramatic happens. There is no brilliant flash illuminating the darkness. No ripple races outward through space. No invisible pulse streaks toward its distant companion. The universe remains astonishingly quiet. And yet, when scientists later compare measurements made on both particles, they discover that the relationship between them is exactly what quantum mechanics predicted. It is almost as though the two particles never fully became separate objects in the first place. That possibility feels deeply unsettling because your entire life has been built upon the opposite assumption. Everything around you appears separate. The book resting on your bedside table seems independent of the moon. The moon seems independent of the Andromeda galaxy. Each object occupies its own place in space, following its own history through time. Distance appears to create individuality. The farther apart things become, the less they seem to share. But perhaps that intuition belongs only to the world of everyday experience. Imagine looking at an enormous tapestry from only a few centimeters away. You might focus on a single thread, believing it exists entirely on its own. Only by stepping back do you discover that every thread contributes to a much larger pattern. Perhaps reality is something like that. Perhaps the universe appears divided because you experience only a tiny part of it. On the deepest quantum level, the separations that seem so obvious to you may not be quite as fundamental as they appear. That does not mean everything is secretly one object. Nor does it mean every particle in the universe is entangled with every other. Quantum entanglement is delicate. It can be created under specific conditions, and it can also be destroyed surprisingly easily when particles interact with their surroundings. In a sense, entanglement is less like tying two knots together forever and more like preserving an incredibly fragile harmony between them. Imagine two perfectly tuned tuning forks. Strike one, and under the right conditions, the other begins to vibrate in sympathy. The analogy is not perfect. Entanglement is stranger than resonance, but it hints at an important idea. The relationship matters more than the individual objects. Physicists have gradually come to realize that this way of thinking appears throughout quantum mechanics. Sometimes the properties of the whole system are more fundamental than the properties of its individual parts. That idea quietly challenges one of your oldest habits of thought. From childhood, you've learned to understand the world by breaking it into pieces. Atoms build molecules. Molecules build cells. Cells build living creatures. Understand the pieces and you understand the whole. Quantum physics gently whispers that, sometimes, the whole possesses qualities that cannot be fully understood by studying the pieces alone. It is a subtle shift in perspective. Yet it may be one of the most profound shifts modern science has ever asked you to make. As you drift peacefully through this imagined universe, watching two tiny particles separated by distances that stretch beyond comprehension, you may begin to sense that the real mystery is no longer whether they remain connected. The deeper mystery is this: what does it actually mean for two things to be separate in the first place? The question you've arrived at is deceptively simple. What does it actually mean for two things to be connected? Your intuition immediately reaches for familiar answers. A bridge connects two cliffs. A road connects two cities. A beam of light connects a distant star to your eyes. Every connection you've ever experienced has involved something traveling across space. Quantum entanglement asks you to let go of that picture. Not because it is wrong, but because it belongs to a world much larger than atoms. A world where everyday experience is an excellent guide. The quantum world, however, follows rules that are quieter, stranger, and far less intuitive. Imagine returning to those two particles one last time. They were created together in a single event. For a brief moment, it doesn't even make sense to describe one without describing the other. They are part of one shared quantum state. That phrase can sound intimidating, but the idea itself is surprisingly gentle. Think of a melody. If someone plays only one note, it has meaning, but it is incomplete. The beauty of the melody doesn't belong to any single note. It belongs to the relationship between all of them. Entangled particles are a little like that. The most important information is not contained entirely within either particle by itself. It exists in the relationship they share. This is why physicists often describe the pair as a single quantum system, even when enormous distances separate them. That sentence is easy to say. It is much harder to truly picture. Your everyday experience insists that objects become more independent as they move farther apart. Quantum mechanics quietly suggests that distance does not always erase relationships established when particles interact. Notice, however, what this does not mean. It does not mean that one particle is secretly sending instructions across the universe. It does not mean invisible energy is flowing between them. And it certainly does not mean that scientists have discovered a way to communicate faster than light. These are among the most common misunderstandings about quantum entanglement. In fact, one of the remarkable achievements of modern physics is showing that entanglement and Einstein's theory of relativity can both be true at the same time. Relativity tells you that no usable information can travel faster than the speed of light. Every experiment ever performed continues to support that principle. Entanglement has never violated it. Instead, entanglement reveals something much more subtle. Imagine flipping two perfectly fair coins in separate rooms. Normally, each result is completely independent. Heads or tails appears at random. Now imagine that every single time you later compare your results, you discover a pattern that should have been impossible if the coins had truly behaved independently. That is closer to what physicists observe. Each individual measurement appears random. You cannot control the outcome. You cannot decide what the particle will do. Only when both observers later compare their measurements does the extraordinary relationship reveal itself. It is almost like reading two separate pages of a novel. Individually, each page seems confusing. Only when you place them side by side does the hidden story emerge. This is why entanglement feels so different from ordinary communication. Nothing obvious passes between the particles at the moment of measurement. Instead, the connection already exists within the quantum description of the pair itself. For many decades, this idea felt deeply unsatisfying. Scientists naturally wanted a picture they could visualize. Something mechanical. Something familiar. Some tiny messenger racing invisibly through space. But every experiment continued pointing in the same direction. The mathematics described reality with astonishing accuracy, even if everyday intuition struggled to follow. Perhaps that says less about the universe, and more about us. After all, your brain did not evolve to understand quantum mechanics. It evolved to throw stones, climb trees, recognize faces, and judge distances across a landscape. The world of atoms is unimaginably smaller than anything your ancestors ever needed to experience. Why should intuition, shaped over millions of years of survival on Earth's surface, perfectly describe the deepest foundations of reality? In a way, it would be more surprising if it did. This realization can be strangely comforting. You do not need to force the universe into familiar shapes. You are allowed to admit that reality is richer than ordinary experience. Science has done this many times before. The Earth feels flat beneath your feet, yet it is curved. The sun appears to move across the sky, yet it is the Earth that rotates. Solid objects feel completely motionless, yet every atom inside them vibrates continuously. Again and again, nature has shown that appearances are not always the whole story. Quantum entanglement may simply be another invitation to look a little deeper. Not to abandon common sense, but to recognize where its limits begin. And as physicists accepted that entanglement was not merely a mathematical curiosity but a genuine feature of the universe, an even more astonishing question slowly emerged. If these mysterious quantum relationships are real, could they actually be useful? Could the very phenomenon that once seemed to threaten our understanding of reality become one of the most powerful tools humanity has ever discovered? The answer would lead scientists toward ideas that once belonged entirely to science fiction. Ideas involving teleportation, unbreakable encryption, and computers unlike anything ever built. And all of them would begin with the same quiet, invisible connection between two tiny particles drifting through the darkness. Imagine that, somewhere in the distant future, humanity has finally spread beyond the solar system. Cities shimmer beneath alien skies. Vast spacecraft drift silently between the stars. Entire generations are born without ever seeing Earth except as a tiny blue point in old photographs. The nearest colony lies 4 light-years away. Another is 30 light-years distant. Some explorers have ventured hundreds of light-years into the darkness, carrying with them everything they need to survive. The universe has become humanity's new ocean. Yet one old problem has never disappeared: distance. Even with astonishingly advanced technology, no message can outrun light. If someone standing on a distant planet sends you a simple greeting, you might wait decades before hearing it. A conversation becomes impossible. You ask a question. Years pass. Eventually the answer arrives. By then, your own life may have changed completely. Perhaps you've moved to another world. Perhaps you've grown old. Perhaps the person who sent the reply is no longer alive. Space is beautiful, but it is also patient. Everything happens slowly. Now imagine someone approaches you with an extraordinary proposal. What if, they say quietly, we already have a way around this problem? Not warp drives. Not wormholes. Not mysterious alien technology. Something much smaller. A pair of entangled particles. Suppose you keep one particle here on Earth while another travels aboard a spacecraft to the nearest star. If measuring one particle immediately determines something about its distant partner, could you use that connection to send messages instantly? At first, the idea feels almost irresistible. You might imagine assigning meanings to the measurements. One result could mean yes. Another could mean no. An explorer stranded on a distant planet could communicate with Earth immediately, no matter how many light years separated them. The loneliness of interstellar travel would disappear overnight. Families scattered across the galaxy could speak as though they were sitting in the same room. Emergency warnings could cross unimaginable distances in an instant. Human civilization itself would be transformed. If such communication were possible, the universe would suddenly feel much smaller. For decades, this possibility fascinated scientists, science fiction writers, and dreamers alike. It still does. Because if entanglement truly connects distant particles in the way experiments suggest, why shouldn't it also carry information? The question seems perfectly reasonable. In fact, it is exactly the question many physicists asked when quantum entanglement was first being explored. Imagine sitting in a laboratory after reading the latest experimental results. You have just learned that two particles continue displaying astonishing correlations across enormous distances. Naturally, your next thought is simple. Can we use this? Science has a long history of turning strange discoveries into revolutionary technologies. Electricity once seemed little more than a scientific curiosity. Today it powers nearly every moment of modern life. Lasers were once described as a solution looking for a problem. Now they quietly operate inside internet cables, supermarket scanners, hospitals, factories, and spacecraft. Even quantum mechanics itself has already given humanity transistors, modern computers, GPS systems, MRI scanners, and countless other inventions that quietly shape everyday life. So perhaps entanglement is simply the next great technological leap. Perhaps someone just hasn't figured out how to use it yet. The idea becomes even more tempting when you remember how extraordinary the experimental results are. Again and again, two distant particles behave in ways that seem mysteriously coordinated. Again and again, Bell's inequalities are violated. Again and again, Einstein's hidden variable explanation fails. Surely you think there must be some kind of connection. And if there is a connection, why shouldn't information travel through it? As you drift through this thought experiment, imagine holding one of the particles gently in your hand. Not literally, of course, it is far too small for that, but imagine that somehow you could. Far away, beyond stars whose light has taken centuries to reach Earth, another observer holds its partner. The two of you agree on a simple plan. If I want to send the number 1, you say, I'll measure my particle now. If I want to send the number 0, I'll wait. It seems wonderfully simple. elegant even. You perform the measurement. Then you wait. Surely on the distant world something must change. Surely the other observer can look at their particle and immediately know what you've done. But as they perform their own measurement, something unexpected happens. They don't receive a message. They don't see a signal. They don't detect an obvious change at all. Instead, they observe something that appears completely random. Heads, tails, down. One outcome is no more predictable than the other. From their perspective, nothing unusual has happened. The extraordinary connection between the particles is still there, but it refuses to behave like a telephone. It refuses to carry a sentence. It refuses to transmit even a single bit of information. It is almost as though nature has placed a quiet lock on one of its deepest mysteries. The particles remain connected. The experiments remain correct. And yet the universe seems determined to prevent anyone from using that connection to outrun light itself. What invisible rule preserves Einstein's cosmic speed limit, even while entanglement continues to challenge your intuition? The answer turns out to be one of the most subtle ideas in all of modern physics, and understanding it reveals that quantum entanglement is, in many ways, even stranger than instant communication itself. At first, the result feels almost disappointing. After everything you've discovered so far, you might have expected quantum entanglement to unlock a completely new way of communicating across the universe. Instead, nature seems to whisper a gentle but firm no. To understand why, imagine returning to those two distant observers. One remains on Earth. The other waits patiently on a planet orbiting a star many light years away. Each holds one particle from an entangled pair. You decide to measure your particle first. The moment you do, you see a result. Perhaps it appears as up. You naturally wonder whether your distant companion has just seen something change. But from their perspective, nothing remarkable has happened. They measure their own particle and receive a result that appears completely random. If they repeat the experiment tomorrow, the outcome still appears random. Again, and again, and again. No hidden message begins to emerge. No pattern spells out words. No sequence of measurements reveals whether you measured your particle an hour ago, a week ago, or not at all. To the distant observer, the results simply look like chance. This is one of the most beautiful tricks nature ever plays. The extraordinary connection only becomes visible after both observers compare their measurements. Imagine each observer keeping a notebook. Every time they measure a particle, they write down the result. Months later, after exchanging those notebooks using an ordinary radio signal, or perhaps by physically carrying them across space, they place the pages side by side. Only then does the hidden pattern appear. Line after line. Measurement after measurement. The correlations fit together with astonishing precision, exactly as quantum mechanics predicted. Individually, each notebook looked like meaningless randomness. Together, they reveal an invisible structure. It is rather like receiving two halves of a photograph. Each half on its own appears confusing and incomplete. Only when they are placed together does the full image emerge. That simple fact changes everything. Because if you cannot control the result of your own measurement, then you cannot use it to send information. You cannot decide whether your particle will appear up or down. Nature chooses. You merely observe. And because you cannot choose the outcome, you cannot encode a message inside it. This idea is known as the no communication theorem. The name sounds technical, but its meaning is surprisingly straightforward. Quantum entanglement creates powerful correlations between distant particles, but those correlations can never be used to transmit usable information faster than light. In other words, the universe permits connection, but not communication. That distinction is subtle. Yet it preserves one of Einstein's greatest discoveries. Relativity remains intact. Light is still the fastest messenger in existence. No signal outruns it. No civilization can use entanglement as an interstellar telephone. No one can warn a distant colony of danger before light itself could carry the message. The speed limit of the universe quietly survives. And somehow, entanglement survives with it. For many physicists, this is where the mystery becomes even deeper. If no information is traveling, then what exactly is happening? It is tempting to imagine invisible waves passing silently through space. But every careful experiment argues against that picture. Nothing measurable leaves one particle and races toward the other. Nothing crosses the distance between them. The mathematics simply describes one shared quantum system whose correlations become apparent only when the observations are compared. In a way, the mystery has shifted. The question is no longer, how fast is the message traveling? The question has become, why does reality possess these correlations in the first place? Some physicists have compared entanglement to reading the final chapter of a mystery novel before you've read the beginning. The ending clearly fits. Every clue makes sense. But you still cannot explain how the story arrived there. Quantum mechanics predicts the ending perfectly. Understanding what that ending says about reality remains one of the deepest challenges in modern physics. Perhaps the most surprising part is that scientists have gradually learned to embrace this uncertainty. There was a time when many believed that every strange feature of quantum mechanics must eventually disappear beneath a more familiar explanation. Decades of increasingly precise experiments have not supported that hope. Instead, they have encouraged researchers to ask an entirely different question. Rather than forcing the universe to behave according to everyday intuition, perhaps everyday intuition is simply too limited. After all, your senses evolved to navigate forests, oceans, mountains, and open skies. They never evolved to understand particles smaller than atoms or distances measured in billions of light-years. The quantum world owes you no obligation to feel familiar. And yet, despite its strangeness, it is astonishingly reliable. Every laser beam, every semiconductor chip, every MRI scanner, every atomic clock, every GPS satellite quietly depends upon the same quantum rules that once seemed too bizarre to believe. The strange mathematics works because nature works that way, whether or not it aligns with human intuition. As you drift a little deeper into this journey, you may notice something quietly changing. At the beginning of the evening, quantum entanglement may have seemed impossible. Now, perhaps it feels less impossible and more mysterious. You no longer need faster-than-light communication for the universe to be extraordinary. The connection itself is extraordinary enough. But if entanglement cannot be used to send messages across the stars, could it still allow something even more remarkable? Over the past few decades, physicists have discovered that this strange quantum relationship can accomplish a task that once belonged entirely to science fiction. Not instant communication, but something that sounds, at first, even more unbelievable. The teleportation of quantum information. And that quiet discovery opens the door to an entirely new chapter in our journey through the hidden architecture of reality. For most of your life, the word teleportation has probably belonged to stories. It brings to mind glowing machines, futuristic spacecraft, or characters who disappear in one place only to instantly appear somewhere else. It is one of those ideas that feels forever trapped in science fiction. And yet, tonight, you're about to discover something quietly remarkable. Because physicists really do use the word teleportation. Not as a metaphor, not as an exaggeration, but as the name of a genuine quantum process that has already been demonstrated in laboratories around the world. The surprising part is that it isn't the kind of teleportation most people imagine. Imagine yourself standing inside a vast observatory late at night. Beyond the enormous glass dome, the sky is perfectly clear. Thousands of stars shine with a steady brilliance, while the pale ribbon of the Milky Way stretches silently across the darkness. Everything feels still, peaceful. You walk toward a small table in the center of the room. Resting upon it is a single quantum particle. It is unimaginably tiny, yet within it exists something incredibly delicate, a complete quantum state. You cannot see this state. You cannot touch it. But it contains all the information that makes this particular particle unique in the quantum world. Now imagine another identical laboratory. Not on the other side of the building. Not even on the other side of Earth. Picture it orbiting a distant planet many light years away. On another table rests another particle. It too waits silently in the darkness. The two laboratories could hardly be farther apart. Between them lie trillions upon trillions of kilometers of empty space. Cold, silent, almost completely devoid of matter. Light itself would need years to travel the distance. And yet physicists ask an extraordinary question. Could the exact quantum state of the particle in front of you somehow appear inside the distant particle, without that fragile quantum information making the journey in the ordinary way? The question sounds almost impossible. Your intuition immediately objects. Information must travel. Every photograph you've ever sent, every email you've written, every conversation you've had has depended upon information moving from one place to another. Whether through electrical wires, radio waves, or pulses of light inside optical fibers, the information always takes a path. It leaves. It travels. It arrives. That rhythm feels almost universal. So when physicists first began discussing quantum teleportation, many people assumed they were proposing something that violated the very foundations of physics. Some imagined people stepping into teleportation machines. Others pictured objects dissolving into energy before reappearing somewhere else in the universe. The reality is quieter, and in many ways even more astonishing. Imagine you are holding a priceless handwritten letter. There is only one copy in existence. Its value lies not in the paper itself, but in the exact arrangement of every word, every sentence, every tiny mark made by the pen. Now imagine that, somehow, the paper in your hands disappears completely, while an identical blank sheet waiting in the distant laboratory suddenly acquires every single word in exactly the same arrangement. The original no longer exists. The new copy is not merely similar. It is identical in every meaningful way. The information has changed location. Not by being copied. Not by being photographed. But by being transferred. That image comes surprisingly close to what quantum teleportation accomplishes. Notice what has not happened. Nothing physical has flown across the galaxy. The particle itself has not traveled through space. Instead, something far more subtle is taking place. The quantum state, the complete description of the particle's condition, is being transferred from one particle to another. If this feels difficult to picture, you're not alone. Even experienced physicists often describe quantum information as one of the most abstract ideas in modern science. Unlike a baseball or a grain of sand, you cannot point to it directly. It doesn't occupy space in the ordinary sense. It describes possibilities, relationships, and probabilities that exist at the deepest level of the quantum world. And somehow, entanglement allows those delicate relationships to be transferred without ever violating Einstein's speed limit. That final detail is crucial. Quantum teleportation is not magic. It does not allow someone to instantly send themselves across the galaxy. It does not allow faster-than-light communication. The universe still insists that ordinary information must obey the cosmic speed limit. And yet, by combining entanglement with ordinary communication, physicists discovered that quantum information itself could perform something that had once seemed unimaginable. It is one of those discoveries that changes the way you think about information itself. Perhaps information is not merely something carried by physical objects. Perhaps, at the deepest level of reality, information is every bit as fundamental as matter and energy. As you gaze upward through the observatory's glass dome, the stars no longer feel quite so distant. Because somewhere beneath their quiet light, hidden within the mathematics of quantum mechanics, lies a process that allows the state of one tiny particle to vanish here and emerge somewhere unimaginably far away. The question is no longer whether such a thing is possible. Scientists have already shown that it is. The real mystery is how they managed to do it, and why the universe permits such a strange process in the first place. Imagine returning to those two quiet laboratories. One rests here on Earth. The other waits beneath an unfamiliar sky, many light years away. Nothing moves between them except silence. No glowing portal opens. No beam of energy stretches across the darkness. If someone were watching from the outside, they would see nothing extraordinary at all. And yet, hidden beneath the ordinary appearance of the experiment, one of the strangest procedures in all of modern physics is about to unfold. The secret begins before the teleportation itself. Long before any information is transferred, scientists prepare something very special. An entangled pair of particles. One particle remains in the first laboratory. Its partner is carefully transported to the second. Only after this shared quantum connection has been established can the experiment begin. Now imagine placing a third particle beside the first. This third particle carries the quantum state you wish to transfer. Perhaps you can think of it as carrying an incredibly delicate melody, one so fragile that trying to copy it directly would destroy it. This is one of the most surprising rules of quantum mechanics. Unlike an ordinary photograph or computer file, an unknown quantum state cannot simply be duplicated. Physicists call this the no-cloning theorem. Nature, it seems, refuses to allow perfect copies of quantum information. There can never be two identical originals. That limitation might sound frustrating. But it is precisely what makes quantum teleportation so remarkable. Instead of copying the information, it transfers it. The original state disappears, while the distant particle takes on exactly the same quantum state. Nothing has been duplicated. Nothing has violated the rules. The information has simply changed its home. Imagine writing a message on the surface of perfectly still water. As one set of ripples fades away, an identical pattern appears somewhere else on another calm lake. The water itself never traveled. Only the pattern has moved. The comparison isn't perfect, but it captures something important. In quantum teleportation, what matters is not the particle itself. It is the quantum information it carries. To make this happen, scientists perform a special joint measurement involving the original particle and one member of the entangled pair. The moment this measurement takes place, the original quantum state is destroyed. It no longer exists where it began. At first this might seem like failure. After all, haven't you just lost the very thing you hoped to preserve? But this is where the experiment takes its remarkable turn. The measurement produces a small amount of ordinary information, just enough to describe what happened during the interaction. That ordinary information is then sent to the distant laboratory using completely conventional communication. Perhaps by radio. Perhaps through an optical fiber. Perhaps by a beam of light traveling through empty space. Whatever method is used, it can never exceed the speed of light. Einstein's cosmic speed limit remains untouched. When that classical information finally arrives, the distant scientist performs one final operation on their particle. It is a tiny adjustment, almost insignificant. And suddenly, the distant particle assumes exactly the quantum state once possessed by the original. The transfer is complete. Nothing material has crossed the enormous distance. Yet something profoundly important has. The quantum state has left one particle and appeared in another. It is one of those moments where language begins to struggle. Was anything actually transported? In one sense, no. The particle remained exactly where it always was. In another sense, absolutely. The information that defined the particle's quantum identity now exists somewhere entirely different. This is why physicists chose the word teleportation. Not because matter disappears and reappears, but because the essential quantum description has been faithfully relocated without ever making the journey in the ordinary way. As astonishing as this sounds, it is no longer merely a theoretical idea. Scientists have demonstrated quantum teleportation many times. First across laboratory benches, then across university campuses, later across cities using optical fibers. Eventually, researchers achieved quantum teleportation between ground stations and orbiting satellites, allowing delicate quantum states to be transferred across more than 1,000 kilometers. Each successful experiment quietly confirmed that the strange rules of quantum mechanics remain astonishingly reliable, even across enormous distances. You may wonder whether this means people could someday be teleported as well. It is an understandable question. But the answer reveals just how unimaginably complex the human body truly is. Every person is made of roughly 37 trillion cells. Each cell contains countless molecules. Each molecule contains atoms. And each atom exists in an incredibly delicate quantum state. To teleport a single human being exactly would require describing, and faithfully transferring, an amount of quantum information so vast that it defies imagination. Even if such a process were physically possible, it lies unimaginably beyond anything current technology could accomplish. For now, teleportation remains the domain of tiny quantum systems. Yet that does not make it any less extraordinary. Because every successful experiment reminds us of something quietly profound. The universe permits forms of information processing that everyday intuition never prepared us to imagine. And researchers are only beginning to explore what these strange capabilities might eventually become. Quantum teleportation is already helping scientists develop entirely new forms of communication and computation. It may one day become part of a global quantum internet, where entangled particles allow quantum information to be shared securely between distant locations. Unlike today's internet, which moves ordinary bits, zeros and ones, a quantum network would exchange fragile quantum states themselves. The engineering challenges remain enormous, but the foundations have already been laid. As you let your thoughts drift beneath the stars once more, notice how far this journey has taken you. Only a short while ago, entanglement seemed like little more than an impossible curiosity. Now it has become the foundation for technologies that laboratories around the world are actively building. And yet, perhaps the most astonishing implication still lies ahead. Because if entanglement can connect particles, if it can preserve delicate quantum relationships across extraordinary distances, then perhaps those connections are doing far more than helping scientists build new technologies. Perhaps they are woven into the very fabric of reality itself. And that possibility leads us toward one of the boldest ideas in modern theoretical physics. What if space itself is built from quantum entanglement? Imagine opening your eyes in a place where there is nothing. No stars. No planets. No galaxies. Not even the faint background glow that fills the emptiest regions of our universe. You are floating in perfect darkness. For a moment, it feels as though you have somehow traveled beyond everything that exists. But then, slowly, tiny points of light begin appearing around you. One, then another, then thousands. Each represents a single particle. At first, they seem completely independent. Tiny islands scattered across an endless sea of darkness. But as you look closer, something begins to change. Faint connections appear between them. Not physical threads. Not beams of light. Simply relationships. Some particles are connected strongly, others only weakly. New particles interact and become entangled. Old relationships fade as the surrounding environment interferes. Gradually, the darkness fills with an unimaginably complicated web of quantum connections. You begin moving backward. The particles shrink beneath you. Atoms appear. Then molecules. Clouds of gas begin gathering beneath the pull of gravity. Stars ignite. Galaxies emerge from the darkness. Soon, you are looking down upon something resembling the universe you know. Billions of galaxies scattered across an enormous cosmic web. But now you can imagine something that was invisible before. Beneath the familiar universe of stars and planets lies another kind of structure. A hidden landscape of quantum relationships. The idea raises an extraordinary question. Could the universe itself be entangled? To answer it, you first need to let go of one common misunderstanding. Entanglement is not an unusual trick that occurs only when scientists carefully prepare particles inside laboratories. It is a natural consequence of quantum mechanics. Whenever quantum systems interact in the right way, they can become entangled. And the universe is filled with interactions. Particles collide. Atoms absorb light. Electrons exchange energy. Radiation passes through matter. Everywhere you look, quantum systems are constantly meeting one another. In the early universe, this was even more extreme. Imagine traveling backward through cosmic history. Galaxies dissolve. Stars fade away. Planets disappear. The universe becomes hotter and denser. Continue backward billions of years, until you arrive at a time when the entire observable universe was compressed into an unimaginably hot, energetic state. Everything you see around you today was once far closer together. The atoms in your body. The material inside distant stars. The particles drifting through galaxies billions of light years away. All of it traces its history back to that early universe. And during those earliest moments, quantum effects were everywhere. This means that, in principle, enormous regions of the cosmos may carry traces of quantum relationships established long ago. That doesn't mean the particle inside your hand is conveniently entangled with a specific particle on the opposite side of the observable universe in a way you could easily measure. Reality is far messier than that. Entanglement is extraordinarily fragile. The moment a quantum system interacts with its environment, its delicate relationships become distributed among countless surrounding particles. This process is known as decoherence. You can imagine it like dropping a single drop of ink into an ocean. At first, the drop is easy to identify. It has a clear shape, a location, a boundary, but gradually the currents pull it apart. The ink spreads farther and farther until its molecules are distributed across an enormous volume of water. The information hasn't necessarily vanished. It has simply become so widely dispersed that reconstructing the original drop becomes practically impossible. Something similar happens to quantum information. A particle interacts with another particle. Then that particle interacts with something else. The relationships spread outward. Soon, the original quantum state becomes entangled with an unimaginably complicated environment. A table, the air, the light bouncing around your room, even you. On some level, the quantum systems that make up your body are constantly interacting with the universe around you. And yet you do not experience yourself as a blurry quantum cloud. You feel solid, definite. Here. The chair beneath you stays where it is. Your bedroom does not appear in two places at once. The world feels reassuringly classical. Decoherence helps explain why. The larger and more complicated a system becomes, the harder it is to isolate from its environment. Tiny quantum effects become distributed across countless interactions until the strange possibilities of the microscopic world effectively disappear from ordinary experience. But this creates a fascinating shift in perspective. Perhaps entanglement does not simply disappear. Perhaps it spreads. Imagine throwing a pebble into a perfectly still pond. The original disturbance begins in one tiny location. Then ripples move outward. They overlap with other ripples. The simple pattern becomes increasingly complex. Eventually, looking at one small patch of water tells you almost nothing about where the disturbance began. The information has become part of something larger. Now imagine this happening throughout the universe. Not with water. With quantum relationships. Every interaction adds another thread. Every collision creates another connection. Every exchange of energy alters the pattern. Over billions of years, the web becomes unimaginably complicated. And this leads to an idea that is both beautiful and deeply strange. Perhaps you cannot fully describe the universe by listing all the things inside it. Perhaps you also need to describe the relationships between those things. Think about a city viewed from high above. You could list every building, every road, every person, every vehicle, but even a perfect list would miss something essential. A city is not merely its objects. It is also the connections between them. Roads connect neighborhoods. Power lines connect buildings. Conversations connect people. Information flows invisibly through millions of relationships. Remove every connection while leaving the individual pieces behind, and the city would no longer truly be a city. Some physicists have begun wondering whether reality itself works in a strangely similar way. What if the relationships between quantum systems are not merely secondary features of the universe? What if they are fundamental? What if space, the very thing that seems to separate one object from another, somehow emerges from these hidden connections? At first, the idea sounds backward. You naturally imagine that space must exist first. Then particles are placed inside it. Then those particles interact and become entangled. Space seems like the stage. Matter and energy are the actors. But modern physics has repeatedly taught us to be careful with stages. Einstein already showed that space is not a passive background. It bends, it stretches, it responds to matter and energy. Perhaps the story goes deeper still. Perhaps spacetime itself is not the most fundamental layer of reality. Perhaps if you could travel far enough beneath atoms, particles, and even quantum fields, you would eventually discover that space is built from something more abstract. Information, relationships, entanglement. You are now approaching one of the most speculative but fascinating frontiers in theoretical physics. A place where quantum mechanics and gravity begin quietly reaching toward each other. Where black holes become laboratories for understanding information. And where some researchers have proposed an idea that sounds almost impossible when you first hear it. Two entangled particles. And 2 points connected by a wormhole. May be different expressions of something deeper. The idea has a deceptively simple name. ER equals EPR. And if even part of it is correct, then the strange connection Einstein once dismissed as spooky action at a distance may turn out to be connected to the very reason distance exists at all. ER equals EPR. At first, those letters tell you almost nothing. But hidden inside them are two of the strangest ideas Einstein ever helped bring into physics. The first, EPR, should now feel familiar. Einstein, Podolsky, Rosen. The three physicists who, in 1935, described the paradox that would eventually become inseparable from our understanding of quantum entanglement. But that same year, Einstein worked with another physicist, Nathan Rosen, on something completely different. Together, they explored a strange mathematical possibility hidden inside general relativity. A bridge through spacetime. Today you might know the general idea by a more familiar name. A wormhole. In the language of physics, the original Einstein-Rosen bridge is represented by the letters ER. For most of the 20th century, these two ideas seemed completely separate. ER belonged to gravity. EPR belonged to quantum mechanics. One described the strange geometry of spacetime. The other described mysterious correlations between particles. There seemed to be no reason they should have anything to do with each other. Then, in 2013, physicists Juan Meldacena and Leonard Susskind proposed something extraordinary. Perhaps they are connected. Perhaps, in some deep mathematical sense, ER equals EPR. To understand how strange this suggestion really is, imagine returning to your two entangled particles. One remains beside you. The other drifts farther and farther away. Eventually, entire galaxies lie between them. From the perspective of ordinary space, the particles are unimaginably distant. Yet their quantum states remain correlated. Now imagine that beneath the reality you can see, there is another description of this relationship. Instead of saying that the particles are mysteriously entangled across space, perhaps you could describe them as connected by an extremely tiny, non-traversable wormhole. A bridge hidden within the deeper geometry of spacetime. Before your imagination runs too far, there is something important to clarify. This does not mean that every pair of entangled particles contains a science fiction tunnel you could fly through. You cannot shrink yourself down and travel from one particle to another. The wormholes involved in these theoretical ideas would not provide shortcuts for people, spacecraft, or messages. They would not allow faster-than-light communication. ER equals EPR remains a theoretical proposal, not an experimentally established fact about ordinary entangled particles. But the possibility points towards something much deeper. Entanglement and geometry may be two different ways of describing the same underlying structure. Imagine holding a sheet of paper. Draw two dots far apart. From the perspective of the flat surface, the dots are separated by a large distance. Now fold the paper. Suddenly the 2 points sit beside each other. The analogy is imperfect, but it reveals something important. Distance depends upon geometry. Change the geometry, and your understanding of separation changes with it. Now go one step further. What if geometry itself depends upon entanglement? What if quantum connections do not simply stretch across pre-existing space? What if, in some sense, they help create the structure you experience as space? This is where the journey becomes truly strange. Imagine removing entanglement from the universe. Not just from one pair of particles. From everything. One by one, the invisible quantum relationships begin disappearing. At first, perhaps nothing seems to change. Stars continue shining. Galaxies remain suspended in darkness. You still feel the ground beneath your feet. But as more and more entanglement disappears, the deeper structure of reality begins to unravel. In certain theoretical models studied by physicists, reducing entanglement between regions of a quantum system can correspond to spacetime itself becoming disconnected. The geometry stretches. Regions move apart. Eventually, the bridge between them disappears entirely. It is almost as though entanglement acts like invisible stitching holding pieces of spacetime together. Remove enough stitches, and the fabric separates. Again, this picture comes from specific theoretical frameworks, not a complete proven description of our universe. But the implications are profound. For most of human history, space seemed like the most fundamental thing imaginable. You can remove every object from a room, yet the empty room remains. Remove the planets from the solar system, and space still seems to exist between the stars. Remove the galaxies, and you imagine an enormous empty universe waiting behind them. Space feels like the container in which everything else exists. But perhaps that picture is backwards. Perhaps space is something that emerges. You already know examples of emergence from everyday life. Consider temperature. A single atom does not really have a temperature in the ordinary sense. Temperature becomes meaningful when enormous numbers of particles move together. Or think about an ocean wave. No individual water molecule contains the wave. The wave emerges from the collective behavior of countless molecules interacting with one another. Perhaps spacetime works in a similarly surprising way. Perhaps no single quantum object contains space. Instead, space emerges from patterns of relationships among vast numbers of quantum systems. If so, then the distance between 2 points might not be the deepest fact about them. Their relationships may come first. Distance may come later. You can almost picture reality as an enormous network. Not a network suspended inside space, but a network from which space itself emerges. Every quantum relationship contributes to the architecture. Every entangled connection helps define which parts of reality are, in some deeper sense, close to one another. The familiar universe of distance and direction could be the large-scale image produced by an unimaginably complex pattern of quantum information. This possibility has become particularly important in the search for a theory of quantum gravity. For more than a century, physics has relied upon two extraordinarily successful theories. General relativity describes the large planets, stars, black holes, the expansion of the universe. Quantum mechanics describes the small atoms, particles, fields, the microscopic foundations of matter. Both theories work astonishingly well. Yet when physicists try to combine them in extreme situations, such as the center of a black hole or the earliest moments of the universe, problems appear. The mathematics stops cooperating. It is as though humanity possesses two pieces of a puzzle that clearly belong together, but no one has yet discovered exactly how they connect. Entanglement may be part of that missing connection. Perhaps gravity and spacetime emerge from deeper quantum information. Perhaps the geometry Einstein described so beautifully is the visible surface of an invisible quantum structure. And perhaps the strange phenomenon that Einstein once hoped would expose the incompleteness of quantum mechanics will ultimately help explain spacetime itself. There is something almost poetic about that possibility. Einstein looked at entanglement and saw a problem, a sign that something was missing. He may have been right. But perhaps what was missing was not a hidden variable restoring the familiar universe. Perhaps what was missing was an even deeper theory, one in which the familiar universe itself emerges from something far stranger. As you imagine the stars above you tonight, you might picture the darkness between them differently. Space no longer needs to feel completely empty. Beneath the silence may lie an invisible architecture of quantum relationships, too small and too subtle for you to perceive directly. Whether spacetime truly emerges from entanglement remains an open question. Physics has not reached the final answer. But even the possibility changes the way you look at the mystery. You began this journey asking how two distant particles could remain connected across space. Now the question has quietly turned itself inside out. Perhaps entanglement does not need to explain how particles connect across space. Perhaps one day, entanglement will help explain why there is space between them at all. And yet, before you drift too far into that possibility, another mystery waits much closer to home. Because everything you've explored so far depends upon a strange moment that keeps appearing throughout quantum mechanics. The moment a measurement is made. A particle exists as a cloud of possibilities. Then you observe it, and somehow you find one definite result. But what does it really mean to observe something? Does your awareness matter? Does consciousness somehow reach into the quantum world and change reality? Or has one of the most famous ideas in popular quantum physics been misunderstood all along? To find out, you have to return from the edge of spacetime and watch a single particle pass through two tiny openings. Imagine that the universe has given you permission to perform one experiment. Not with a giant telescope. Not inside a particle accelerator stretching for kilometers beneath the ground. Your experiment is surprisingly simple. In front of you stands a thin wall. Cut into that wall are two narrow openings. And behind it waits a screen capable of recording anything that arrives. You begin with something familiar. Tiny grains of sand. One by one you gently fire them toward the wall. Most strike the barrier and fall away. A few pass through the opening on the left. Others pass through the opening on the right. Gradually, a pattern appears on the screen behind them. Two bands. Exactly what you would expect. Each grain of sand travels through one opening or the other. There is nothing mysterious here. Now you replace the grains of sand with waves. Imagine gentle ripples moving across perfectly still water. When the waves reach the two openings, something different happens. Each opening creates a new wave. The two sets of ripples spread outward and overlap. Where one crest meets another crest, the waves reinforce each other. Where a crest meets a trough, they cancel. The result is an interference pattern. A series of alternating regions where the waves become stronger and weaker. Again, everything makes sense. Particles create two bands. Waves create interference. Two completely different behaviors. Now imagine replacing the sand and water with something much smaller. Electrons. You fire them toward the wall. One at a time. Slowly. Patiently. An electron leaves your equipment. A moment later, a tiny point appears on the detector screen. Then another electron. Another point. At first, nothing seems unusual. Each electron arrives at one specific location, just as you would expect from a particle. You continue. Hundreds of electrons. Thousands. Tens of thousands. And slowly, something strange begins to emerge. The individual dots form a pattern. Not two simple bands. An interference pattern. The same kind of pattern produced by waves. You stare at the screen. Something seems wrong. You sent the electrons one at a time. There was no second electron nearby for each one to interfere with. So what created the pattern? The mathematics of quantum mechanics offers an answer that sounds almost impossible. Each electron behaves as though its possible paths pass through both openings. The possibilities interfere. Then, when the electron reaches the detector, you observe only one definite location. One tiny dot. Repeat the process enough times, and those individual dots slowly reveal the hidden wave-like pattern beneath them. It is one of the most famous experiments in all of physics, and one of the strangest, but perhaps you think there is a simple explanation. Maybe the electron really does pass through only one opening. You simply don't know which one, so you decide to watch. You place a detector beside the slits. Now, whenever an electron passes through, your equipment can determine which opening it used. Left or right. You begin the experiment again. One electron, then another, thousands more. And when you finally look at the screen, the interference pattern has disappeared. The electrons now behave differently. The moment information about their path becomes available, the wave-like interference vanishes. It is difficult to encounter this experiment for the first time without feeling that something deeply strange has happened. Before you measured the path, the electron behaved as though multiple possibilities mattered. After you measured it, you found a definite path. The natural question almost asks itself, did observation change reality? Popular descriptions of quantum mechanics sometimes take this idea much further. Perhaps they suggest your conscious mind somehow forces the universe to choose. Perhaps reality remains undefined until someone looks. Perhaps the moon itself would become uncertain if nobody were watching it. These ideas are fascinating. They are also misleading. To understand what is really happening, you need to think carefully about the word observation. Because in quantum mechanics, observation does not necessarily mean a human being opening their eyes. The electron does not know that you are watching. It does not become shy beneath the gaze of a scientist. Your consciousness does not need to reach mysteriously into the experiment. Something more physical is happening. To measure which slit the electron passes through, your detector must interact with it. Perhaps a photon of light encounters the electron. Perhaps another particle interacts with it. Some physical process must carry information about the electron's path into the surrounding environment. And the moment that interaction occurs, the experiment has changed. Imagine trying to discover the position of a tiny floating feather in a completely dark room. You cannot see it. So you throw tennis balls into the darkness and listen for one to bounce off the feather. Eventually you locate it. But there is a problem. The tennis ball that revealed the feather's position also disturbed it. Your act of measuring became part of the event. At quantum scales, this relationship between measurement and interaction becomes far more fundamental. But even this analogy does not capture the whole story. The disappearance of interference is not merely about accidentally bumping into a particle. It is about information. When the possible paths of a quantum system become distinguishable, when information about those alternatives becomes encoded somewhere in the environment, the interference between those possibilities can disappear. This process begins leading you toward an idea you've already encountered: decoherence. Imagine the electron's delicate quantum possibilities as perfectly synchronized notes in a quiet piece of music. As long as the system remains isolated, those notes can interfere with one another in precise and beautiful ways. But then the surrounding environment enters. A stray photon interacts with the electron, then another particle, then the detector. The quantum information begins spreading outward into an enormous web of relationships. The delicate synchronization becomes effectively impossible to recover. From your perspective, the strange quantum possibilities seem to disappear, and the familiar classical world begins to emerge. This happens astonishingly quickly for large objects. You never see your bedside table pass through two doors at once. You never wake to find your pillow existing in a visible superposition of opposite sides of the room. Large objects interact constantly with their environments. Air molecules collide with them. Light scatters from them. Heat radiates away. Countless interactions continuously spread quantum information into the surroundings. The fragile conditions required for obvious interference disappear almost instantly. This is why the world around you feels definite, solid, stable, ordinary. And yet, beneath that ordinary appearance, quantum mechanics remains. The atoms inside your body still obey quantum rules. The light entering your eyes is quantum. The chemistry keeping you alive depends upon quantum mechanics. You are not standing outside the quantum universe looking in. You are made entirely from it. Which leaves you with an extraordinary mystery. If everything is quantum at its foundation, how does the definite world you experience emerge from all those possibilities? Decoherence explains an important part of that transition. But depending on how you interpret quantum mechanics, it may not answer every question. Some physicists believe the mystery ends with the mathematics. Others believe something deeper remains unresolved. And this is where the quiet question at the heart of quantum mechanics returns once more. When you perform a measurement and experience one definite result, what exactly has happened to all the other possibilities? What happened to all the other possibilities? It is a remarkably simple question. And after more than a century of quantum mechanics, there is still no single answer that every physicist agrees upon. The equations themselves work beautifully. Give physicists a quantum system, and they can calculate the probabilities of different outcomes with astonishing precision. What the equations do not tell you quite so clearly is what those probabilities actually represent. To understand the mystery, imagine returning to your electron. Before you measure it, quantum mechanics describes the electron using something called a wave function. You cannot hold a wave function in your hand. You cannot photograph one. It is a mathematical description containing information about the possible outcomes of measurements you might perform. Imagine it as a kind of map. Not a map showing where the electron definitely is, but a map describing the possibilities for where you might find it. Some possibilities are more likely, others less likely. And under the right conditions, these possibilities can interfere with one another. That is what you witnessed in the double-slit experiment. Before information about the electron's path became available, the possibilities could interfere. Once the electron became sufficiently entangled with the measuring device and surrounding environment, that interference disappeared from anything you could practically observe. This is decoherence. And it happens constantly. Right now, as you listen to these words, an unimaginably complicated web of interactions surrounds you. Photons of light bounce from walls. Air molecules collide. Heat radiates from your body. Atoms vibrate inside every object nearby. Each interaction quietly carries information into the environment. This is one reason you never experience the obvious strangeness of quantum superposition in everyday life. Your surroundings are simply too interconnected. The quantum world has not disappeared. It has become entangled with everything else. But here is where things become subtle. Decoherence explains remarkably well why interference becomes effectively unobservable in large systems. What it does not necessarily explain all by itself is why you experience one particular outcome. Imagine measuring an electron. The equations may assign probabilities to several possible results. You perform the experiment, and you see one. Why that one? What happened to the others? This is part of what physicists call the measurement problem. And it is here that the popular idea of the observer often creates confusion. You may have heard that consciousness collapses the wave function, that the universe somehow waits for a human mind to look at it, or even that your thoughts directly create physical reality. These ideas appear frequently in popular discussions of quantum mechanics, but they are not conclusions established by quantum experiments. There is no experimental evidence showing that human consciousness is uniquely required for quantum measurement. A detector can record an electron while nobody is in the laboratory. A photon can interact with an atom billions of light years from Earth. Quantum systems have been interacting with their environments for billions of years before humans existed. The universe does not appear to need you to stare at it in order to continue existing. In physics, an observer is often simply another physical system that interacts with the system being measured. A detector can be an observer. An atom can interact with another atom. A photon can carry information away. The important ingredient is not necessarily awareness. It is interaction and the creation of correlations. This distinction removes some of the mystical language surrounding quantum mechanics. But it does not make the underlying mystery disappear. In some ways it makes it even more interesting. Because if consciousness is not responsible for choosing reality, then what is? Perhaps nothing chooses. Perhaps all possible outcomes continue existing in some sense. Perhaps the wave function truly collapses according to rules we do not yet fully understand. Perhaps quantum mechanics is only a description of our knowledge rather than reality itself. Or perhaps the question is based upon an assumption that nature simply does not share. These possibilities lead you into the world of quantum interpretations. And this is where physics begins to feel almost philosophical. Imagine entering a long, quiet hallway. Along it are several doors. Behind every door is a different explanation of what quantum mechanics might actually be telling you about reality. Open the first door, and you find a universe where measurement produces a definite outcome through something often described as wave function collapse. Open another, and you discover a reality where the wave function never collapses at all. Every possible outcome continues. Behind another door, particles follow definite trajectories guided by an invisible quantum wave. Behind yet another, properties may exist only relative to other physical systems. The strange thing is that several of these interpretations can reproduce the same experimental predictions. You perform the experiment. You collect the data. And the interpretations may agree perfectly about what you will observe. They disagree about what is happening beneath the surface. It is like watching shadows moving across a wall while several people offer completely different explanations for what is casting them. Each explanation may reproduce the shape of the shadow. But which one describes the object behind you? Perhaps future experiments will reveal the answer. Perhaps a deeper theory will replace the question entirely. Or perhaps some aspects of reality will always resist the kind of intuitive picture your mind naturally seeks. For now, quantum mechanics continues doing something extraordinary. It works. Its predictions rank among the most accurate ever produced by science. Modern electronics depend upon it. Lasers depend upon it. Much of chemistry depends upon it. And the strange entanglement you've been exploring tonight is not a philosophical curiosity. It is experimentally real. Yet beneath all this extraordinary success lies a question physicists still debate. What is quantum mechanics actually describing? You began with two particles mysteriously connected across distance. You followed Einstein as he challenged the idea. You watched Bell transform philosophy into experiment. You discovered that entanglement cannot send messages faster than light, yet can help teleport quantum information. And then you followed those connections deeper, toward the possibility that entanglement itself may be related to the structure of spacetime. Now you have reached perhaps the strangest point of all. The experiments tell you what happens. The mathematics tells you what to expect. But when you ask what reality is actually doing when nobody is looking, physics offers you more than one answer. And behind the next door waits a possibility that may be stranger than anything you've encountered so far. Perhaps every quantum possibility is real. Perhaps somewhere within the mathematics, nothing is ever truly lost. And perhaps every time the universe appears to choose one outcome, it never actually chooses at all. Imagine standing at the end of that long, quiet hallway. Behind you lies everything you've discovered tonight. Entangled particles, Bell's experiments, quantum teleportation, the strange boundary between possibility and measurement. Ahead of you are 4 doors. Each leads to a different version of reality. And the strangest thing is that, when you perform many ordinary quantum experiments, each door may lead you toward the same observable result. You cannot simply look at the data and immediately know which door is correct. Nature has given you the answer to the experiment, but perhaps not yet the answer to what the experiment means. You approach the first door. Behind it lies the oldest and perhaps most familiar interpretation of quantum mechanics, the Copenhagen interpretation. The name comes from the work associated with physicists such as Niels Bohr and Werner Heisenberg, although there has never been one perfectly defined version accepted by everyone. The basic picture is something like this. Before a measurement, a quantum system is described by a wave function containing different possible outcomes. Then you perform a measurement. You observe one definite result. In traditional descriptions, the wave function is said to collapse. The cloud of possibilities becomes a single observed outcome. Imagine spinning a wheel in complete darkness. Before you turn on the light, you describe several possible positions where the pointer might be. Then the light appears. You see one answer. Except, in quantum mechanics, the uncertainty is not necessarily just about your lack of knowledge. The possibilities themselves are part of the mathematical description. The Copenhagen interpretation tells you how to use that description extraordinarily well. Calculate the wave function. Predict the probabilities. Perform the measurement. Observe the result. For many physicists, that is enough. The purpose of physics, in this view, is to predict what experiments will reveal. You do not necessarily need to imagine some hidden machinery operating beneath the mathematics. But perhaps you feel the same quiet dissatisfaction Einstein once felt. What actually causes collapse? At exactly what point does it happen? When the particle touches the detector. When the detector records the result. When information reaches the environment. The interpretation gives you a practical framework. But depending on how you formulate it, deeper philosophical questions can remain. So you turn toward the second door. You open it, and behind it lies something much larger. Not one definite outcome, but every outcome. This is the many worlds interpretation. It was proposed in the 1950s by physicist Hugh Everett, and its starting point is surprisingly simple. What if the wave function never collapses? Quantum mechanics already contains equations describing how wave functions evolve. Perhaps, Everett suggested, you do not need to add a special collapse process at all. Instead, all possible outcomes remain part of the universal quantum state. Imagine performing a measurement. You observe one result. But according to many worlds, the other possibilities have not simply vanished. Instead, the total quantum state evolves into effectively separate branches associated with different outcomes. In one branch, you observe one result. In another, a different result is recorded. The branches no longer meaningfully interfere with one another because of decoherence. From inside your branch, you experience only your own outcome. This idea is often described dramatically. Every decision creates another universe. Every choice produces a new world. But that popular image can be misleading. Many worlds is not necessarily saying that a brand new physical universe suddenly pops into existence whenever you decide what to eat for breakfast. The idea is more subtle. It says that the quantum state evolves continuously according to the equations, without a special collapse rule, while decoherence produces branches that behave independently for practical purposes. Still, the implications are extraordinary. Imagine the double-slit experiment again. Imagine every quantum event that has occurred since the beginning of the universe. If many worlds is correct, reality may contain an unimaginably vast branching structure of outcomes. Somewhere within that mathematical description are possibilities you will never experience. Not because they disappeared, but because you occupy only one branch. You stand quietly before this second door. The idea is both elegant and overwhelming. It removes the mysterious collapse. But the price seems enormous. Instead of explaining why one outcome becomes real, it suggests that all outcomes remain real within different branches. Is that simpler? Or infinitely more complicated? Physicists disagree. You move toward the third door. Behind it waits an idea that Einstein might have found somewhat more familiar. Particles are real. They possess definite positions. They follow actual paths. This is pilot wave theory, often associated with Louis de Broglie and David Bohm. Imagine an ocean. Across its surface moves a tiny floating object. The object always occupies one definite position, but its motion is guided by the waves surrounding it. In pilot wave theory, quantum particles have definite configurations, while a wave function guides their evolution. The uncertainty you experience does not necessarily mean the particle itself lacks a position. There is a deeper structure beneath the probabilities. At first, this may sound exactly like the hidden variable theory Einstein hoped for. And in some ways it is. But there is a catch. A very important one. Bell's theorem ruled out local hidden variable theories. Pilot wave theory survives because it is explicitly non-local. The behavior of one part of an entangled system can depend on the configuration of distant parts in a way that cannot be reduced to ordinary local influences. Einstein's desire for definite properties may survive behind this door. His commitment to locality does not. You now have three pictures: collapse, branching worlds, particles guided by a non-local wave. Each tells a radically different story about what might exist beneath the same quantum experiments. And there is still another door. Behind it lies an interpretation that asks you to reconsider the idea that objects must possess properties entirely on their own. This is relational quantum mechanics. In this view, the state of a system may be meaningful only relative to another system with which it interacts. There may be no single absolute description of every property from a universal God's-eye perspective. Instead, facts can be relational. Imagine two people standing on different moving trains. Each can correctly describe the motion of the other relative to themselves. Neither perspective must be declared the one absolute viewpoint. Relational quantum mechanics asks whether quantum properties might work in a similarly relational way. A particle may have a definite outcome relative to one system while the larger combined system is described differently relative to another. Reality in this picture becomes less like a collection of objects carrying permanent labels, and more like a web of interactions, relationships, events, information exchanged whenever systems meet. You stand once again in the hallway. 4 doors remain open behind you. Through one, possibilities collapse. Through another, they all continue. Behind the third, particles follow definite paths guided by a non-local quantum structure. Behind the fourth, properties themselves become relational. Which one is real? Perhaps one of them. Perhaps none. Perhaps each captures one fragment of a deeper theory humanity has not yet discovered. And this is where the mystery of quantum mechanics becomes almost unique in science. Physicists can agree with astonishing precision about what the equations predict. They can build technologies using those predictions. They can perform experiments confirming them again and again, and still disagree profoundly about the reality those equations describe. The next step in your journey, then, is not to choose a favorite door. It is to walk through each one a little more carefully. Because when you do, you begin to notice something extraordinary. No matter which interpretation you choose, something about your familiar picture of reality must be surrendered. No matter which door you choose, something familiar seems to disappear. Perhaps that is the quiet lesson hidden beneath the interpretations of quantum mechanics. There is no obvious path back to the universe you once imagined. A universe where every object always possesses a complete set of definite properties. Where distance guarantees independence. Where every event has a single, predictable cause. Where reality unfolds along one clear path from past to future. Quantum mechanics seems unwilling to give you all of those things at once. Imagine returning to the first door. The Copenhagen interpretation. Here, you accept that quantum mechanics gives you probabilities for measurement outcomes. You perform an experiment. You receive one answer. The theory works. You move on. There is something wonderfully practical about this approach. It has allowed generations of physicists to calculate the behavior of atoms, particles, and fields without needing to settle every philosophical question first. And perhaps that is reasonable. After all, you do not need to understand the deepest nature of gravity to know that dropping your phone is probably a bad idea. Sometimes prediction is enough. But if you insist on asking what physically happens during measurement, the picture becomes less comfortable. Why this outcome? Why now? What exactly separates an ordinary quantum interaction from a measurement? Different versions of the Copenhagen tradition answer these questions differently, and some avoid treating collapse as a literal physical event altogether. But the mystery of measurement remains. So you walk through the second door. Many worlds. Here the collapse problem disappears. The wave function simply continues evolving. The mathematics remains smooth. Nothing special needs to happen when you make a measurement, but now you must accept something else. Every possible outcome represented in the quantum state remains within the larger description. You experience one branch. Other outcomes belong to other effectively decohered branches. Imagine standing at the trunk of an enormous tree. Above you, branches divide, then divide again, and again. The farther you look, the more complicated the structure becomes, until the individual branches disappear into something resembling a cloud. Now imagine that branching not across physical space, but within the mathematical structure of the universal quantum state. Every quantum interaction contributes to an unimaginably complex pattern. If this interpretation is correct, then the single reality you experience may be only one perspective within something vastly larger. The idea sounds extravagant, but supporters of many worlds might turn the criticism around. Which is more extravagant? Allowing the equations to evolve exactly as written? Or inventing an additional process called collapse that interrupts them? There is no universally accepted answer, and so you return to the third door. Pilot wave theory. Perhaps here you can recover something closer to classical intuition. Particles have definite configurations. They are not merely clouds of possibility. They follow trajectories. Something exists even when nobody measures it. For Einstein, parts of this picture might have sounded appealing. But Bell's theorem demands a price. Non-locality. The guiding quantum structure does not respect the simple local picture Einstein hoped to preserve. Entangled systems remain connected in a deep mathematical sense. The universe regains definite particle positions, but not the independence of distant systems that classical intuition might prefer. Once again, you are forced to surrender something. Then you enter the final room. Relational quantum mechanics. Here, perhaps the mistake was asking for an absolute description in the first place. You are accustomed to imagining that every object possesses properties entirely on its own. This particle is here. That particle is there. This object has this velocity. That system has that state. But even classical physics has taught you to be careful. Velocity is already relational. You may be sitting perfectly still relative to your bed while moving hundreds of meters per second relative to Earth's axis, tens of kilometers per second around the sun, and far faster relative to distant galaxies. Which velocity is your true velocity? There is no single answer without specifying a reference frame. Perhaps quantum states contain a similar lesson. Perhaps properties become definite only in relation to other physical systems. Reality may not be a giant collection of independently existing labels. It may be a network of relationships. If so, entanglement begins to feel less like an exception. Perhaps relationship was fundamental all along. You have now traveled through 4 different interpretations, and you may have noticed something strange. None of them changes the experimental results you've encountered tonight. Bell's inequalities remain violated. Entanglement remains real. Quantum teleportation still works. The double-slit experiment produces the same patterns. The equations continue making astonishingly accurate predictions. What changes is the story you tell about what is happening underneath. And perhaps this is why quantum foundations remain such an active field of research. The debate is not merely philosophical decoration added to finished physics. Researchers continue searching for new experiments, deeper theories, and subtle differences that might someday distinguish between competing pictures. Some physicists explore modifications of quantum mechanics in which collapse is a genuine physical process. Others investigate whether gravity could play a role. Some study quantum information as a possible foundation for deeper physical laws. Others ask whether spacetime itself emerges from entanglement. The story is not finished. That may be one of the most beautiful things about it. You are living at a time when humanity can manipulate individual quantum systems with extraordinary precision. While still debating what those systems ultimately tell us about reality, you can build a quantum computer without agreeing on the interpretation of quantum mechanics. You can teleport a quantum state without knowing whether the wave function represents a physical object, information, or something else entirely. You can measure entanglement without possessing a universally accepted answer for what the connection truly means. Science does not always progress by solving one mystery before approaching the next. Sometimes it builds reliable islands of knowledge surrounded by deeper oceans of uncertainty. And slowly, patiently, those islands grow. As you leave the hallway behind, perhaps you realize that the most unsettling part of quantum mechanics is not any single interpretation. It is that every serious attempt to understand the theory seems to demand that you abandon at least one deeply intuitive assumption. Maybe outcomes are not definite before measurement. Maybe the wave function never collapses. Maybe distant systems cannot be understood as completely independent. Maybe properties exist only through relationships. Maybe the universe is not fundamentally built from separate things at all. And this brings you back to where your journey began. Two particles, created together, separated by an enormous distance, measured independently, yet correlated more strongly than any local hidden variable theory can explain. After everything you've explored, you can finally ask the question hidden inside the title of tonight's journey. What is the terrifying truth about quantum entanglement? Perhaps it is not that particles communicate faster than light. They don't. Perhaps it is not that your consciousness magically creates reality. There is no evidence that it does. Perhaps it is not even that physics has discovered something supernatural. It hasn't. The deeper truth may be far quieter. The universe works perfectly well, reliably, predictably enough to build experiments and technologies, but it does not seem obligated to resemble the reality your intuition expected. And in the final part of your journey, you are going to gather every strange clue you've encountered tonight and ask one last question. If locality, separateness, and perhaps even spacetime itself are not as fundamental as they appear, then what kind of universe are you actually living in? Imagine returning to the beginning of your journey. Two particles rest quietly beside one another. Nothing about them appears remarkable. They are unimaginably small, invisible to your eyes. Just two tiny pieces of a universe filled with billions of galaxies. Then they begin to separate. One moves in one direction. The other moves away, farther and farther, until an enormous distance lies between them. Perhaps one remains here on Earth while the other travels beyond the solar system. Perhaps centuries pass. Perhaps entire stars lie between them. And yet, when the right measurements are performed, something extraordinary remains. A relationship. A pattern of correlation stronger than any local hidden variable theory can explain. When you first encountered this idea, it sounded almost impossible. Perhaps you imagined some invisible signal racing between the particles. Maybe information was somehow traveling faster than light. Maybe there was a hidden connection scientists simply hadn't discovered yet. Einstein hoped for something like that. He believed quantum mechanics was revealing only part of the picture. Beneath its probabilities, he suspected, there must be a deeper reality. A world of hidden variables. A universe where distant objects possess their own independent properties and nothing could mysteriously influence something else across empty space. It was a reasonable idea. Perhaps even the idea you would have chosen. Then John Bell found a way to ask the universe directly. And nature answered. Again. And again. And again. The correlations predicted by quantum mechanics appeared in experiments. Local hidden variable theories could not reproduce them. The universe refused to return to the simple picture Einstein wanted. But it also refused to give you something easier in its place. Entanglement did not become a faster-than-light telephone. You could not use it to send a message across the galaxy. You could not whisper into one particle and have another repeat your words on the opposite side of the universe. Relativity survived. The speed of light remained the cosmic limit for usable information. And yet the quantum correlations remained. Nothing obvious crossed the distance. No detectable signal made the journey. The relationship simply existed within the quantum description of the system. Perhaps that was the first clue. Maybe the mistake was imagining that the particles needed to send something to each other at all. Maybe their relationship was not a conversation between two completely independent objects. Maybe, at the quantum level, the system could not always be divided into separate pieces in the way your everyday intuition demanded. You continued deeper. You discovered that entanglement could be used for something that once sounded like pure science fiction. Quantum teleportation. Not the transportation of people. Not matter disappearing in a flash of light. Something more subtle. Quantum information transferred from one physical system to another using entanglement together with ordinary classical communication. Once again, the universe preserved its rules. Nothing traveled faster than light. Nothing supernatural occurred. And yet something became possible that classical intuition would never have predicted. Then the journey expanded. From particles to spacetime itself. You encountered the possibility that entanglement may be connected to something far larger than quantum experiments performed inside laboratories. In certain theoretical frameworks, patterns of entanglement appear deeply related to geometry. Some physicists have begun exploring whether spacetime itself could emerge from more fundamental quantum relationships. Perhaps the universe is not fundamentally made from objects placed inside a pre-existing container called space. Perhaps the relationships come first. Perhaps space emerges later. The idea remains speculative. No experiment has established that entanglement literally creates the spacetime of our universe. But the possibility is difficult to forget. Because it quietly reverses your entire picture of reality. You normally imagine distance first. Two particles are separated by space. Then you ask how they remain entangled across that distance. But perhaps, at a deeper level, that question is backwards. Perhaps quantum relationships help define what distance means in the first place. If so, entanglement would not be a strange connection stretching across space. It would belong to the deeper architecture from which your experience of space emerges. Imagine looking at a photograph on a screen. From a distance you see mountains, clouds, a blue sky, perhaps a river winding through a valley. Move closer. The landscape disappears. Now you see pixels, tiny points arranged in an enormous pattern. The mountains were never separate from those pixels. They emerged from them. Perhaps the universe hides a similar change of perspective. From where you stand you see space, distance, objects, people, stars, galaxies. Everything appears separate. But if you could somehow look beneath the deepest layer of physical reality, perhaps the familiar picture would dissolve. Perhaps you would find relationships, information, quantum states, patterns of entanglement so complicated that the universe you experience emerges naturally from them. You might even discover that asking where something is makes sense only after those deeper relationships have been established. This is not something physics has proven, but it is the direction in which some of its deepest questions now point. And that alone is remarkable, because entanglement began as an embarrassment, a paradox, something Einstein and his colleagues hoped would reveal a flaw in quantum mechanics. Instead, it became an experimentally verified feature of nature. Then it became a resource. Scientists learned to manipulate it, measure it, use it for quantum information. And now it appears in some of the deepest attempts to understand black holes, gravity, information, and the possible quantum foundations of spacetime. The problem did not disappear. It grew. Not because physics failed, but because every answer revealed a larger question beneath it. You saw the same pattern when you explored measurement. The double-slit experiment seemed to ask whether observation creates reality. But the deeper answer was more careful. Human consciousness does not appear to possess some magical power over particles. Measurement involves physical interaction. Quantum systems become entangled with detectors and environments. Decoherence spreads quantum information into surroundings so complicated that interference between different possibilities becomes effectively impossible to observe. The strange quantum world gives rise to the stable classical world you experience. But even then, one mystery remained. Why do you experience one outcome? What happens to the other possibilities? And once again, physics offered several doors. Behind one was collapse. Behind another were branching worlds. Behind another, particles guided by a non-local quantum structure. Behind another, a reality defined through relationships between physical systems. Different interpretations. Different pictures. The same extraordinary experimental predictions. Perhaps one will eventually prove correct. Perhaps a future theory will reveal that all of them were incomplete. But something important remains true regardless of which interpretation you prefer. Quantum entanglement is not an illusion. The Bell test experiments are real. The correlations are real. And the classical idea of a universe governed entirely by local hidden variables does not match what nature has shown us. This is where you finally begin approaching the terrifying truth. And perhaps the word terrifying is slightly misleading. There is nothing here to fear. The stars will continue shining. The earth will continue turning. Your room will remain exactly where it is. The laws of physics are not breaking around you. Quite the opposite. They are working perfectly. The unsettling part is simply that reality appears to be under no obligation to match the picture your mind naturally creates of it. You evolved inside a world of medium-sized objects moving at slow speeds. You learned that things are separate. That objects have definite positions. That causes happen before effects. That distance divides one place from another. Those intuitions work beautifully in everyday life. But you have spent tonight traveling far beyond the world in which those intuitions evolved. And there, at the deepest scales of nature, the universe seems to follow a different kind of logic. Not an illogical one. Not a supernatural one. Simply one that feels unfamiliar. Perhaps the terrifying truth about quantum entanglement is not that the universe contains some impossible secret connection. Perhaps it is that the separateness you experience every day may not belong to the deepest layer of reality at all. You look around and see individual things. Separate objects. Separate places. Separate moments. But beneath them may lie a reality defined less by things themselves, and more by the relationships between them. And if that possibility is even partly correct, then the final question is no longer simply how two particles can remain connected. The final question is much larger. What if connection is fundamental? and separation is what emerges? What if connection is fundamental, and separation is what emerges? You can allow that question to remain unanswered for a moment. There is no need to solve it tonight. Physics certainly hasn't. Perhaps the most honest place to end this journey is not with certainty, but with the boundary between what humanity knows and what remains hidden. Because after everything you've explored, there are some things you can say with remarkable confidence. Quantum entanglement is real. It has been observed, tested, measured, again and again. Bell's inequalities have been violated in carefully controlled experiments, ruling out broad classes of local hidden variable explanations. Entangled systems display correlations that cannot be explained by the simple idea that each particle carried a complete set of local instructions from the moment they separated. And yet, those correlations cannot be used to send information faster than light. Einstein's cosmic speed limit remains intact. No message flashes instantly across the universe. No signal outruns a photon. Relativity continues to describe spacetime with extraordinary precision. Somehow nature accommodates both quantum entanglement and the speed limit of light. At first, these ideas seem to pull reality in opposite directions. One suggests a strange kind of connection across distance. The other insists that information cannot cross that distance instantaneously. But perhaps the contradiction exists only because you are trying to picture the quantum world using concepts borrowed from everyday life. Maybe the particles aren't sending anything. Maybe nothing travels. Maybe the correlation does not need to cross space because it belongs to the quantum system as a whole. You might imagine two distant notes belonging to the same piece of music. The notes do not need to communicate with each other to belong to the same melody. Their relationship exists because of the structure of the composition itself. The analogy is imperfect. Every analogy for quantum mechanics eventually is. But perhaps it points toward something useful. You naturally divide reality into objects. This particle, this person, that star, this galaxy, that distant world. You draw invisible boundaries around things and give them names. It is one of the ways your mind makes sense of an unimaginably complicated universe. And on the scale of everyday life it works beautifully. But quantum mechanics suggests that nature may not always respect those boundaries in the way you expect. An entangled system can possess properties that belong to the relationship between its parts rather than to either part independently. The whole contains information that cannot be reduced to a simple list describing each piece on its own. That is not philosophy. That is part of the mathematical and experimental structure of quantum theory. What it ultimately means for reality is where interpretation begins. Perhaps one day physicists will discover a deeper theory. A theory from which both quantum mechanics and gravity emerge naturally. A theory that explains entanglement without mystery. Perhaps future scientists will look back at the questions you're considering tonight in the same way you now look back at ancient debates about the motion of the planets. What once seemed incomprehensible may eventually appear obvious. Or perhaps the answer will be stranger than anything humanity has imagined. You can picture a scientist hundreds of years from now. Perhaps they live on Earth. Perhaps somewhere else. They sit beneath a sky filled with stars, just as people have done for thousands of years. But their understanding of those stars, and the space between them, is completely different from yours. Maybe by then, quantum gravity has been understood. Perhaps spacetime has been revealed as an emergent phenomenon. Maybe physicists have discovered that information is more fundamental than matter. Perhaps ER equals EPR was one small clue pointing toward something much larger. Or perhaps all of these ideas have been replaced by a theory whose concepts you would barely recognize. Science has a habit of doing that. Every generation believes it has reached something close to the foundations. Then someone asks a better question. Newton gave humanity gravity. Einstein transformed gravity into geometry. Quantum mechanics transformed particles into something far stranger than tiny objects. And entanglement forced physicists to reconsider what it means for distant systems to possess independent realities. The universe did not become less understandable. It became deeper. That distinction matters. Mystery does not mean failure. Not knowing is not the same as knowing nothing. You know far more about quantum entanglement today than Einstein could have known when he first described it as spooky. You can create entangled particles deliberately. You can measure them. You can test Bell inequalities. You can teleport quantum states. Researchers can distribute entanglement across enormous distances and explore its use in quantum networks. The mystery has become something you can touch experimentally. And perhaps that is one of the most beautiful things science can do. It takes something that sounds impossible and makes it measurable. You began tonight with two particles. Two tiny objects separated by distance. The mystery seems simple. How could one know what happened to the other? But slowly that question changed. You learned that knowing was the wrong word. The particles were not conscious. They were not sending secret messages. They were not breaking the speed of light. They were simply part of a quantum system whose correlations could not be reproduced by local hidden variable theories. Then the question changed again. What does it mean for two things to be separate? And then again, what if spacetime itself is not fundamental? And finally, what kind of reality produces all of this? There is no final answer. Not yet. And perhaps, as you lie quietly in the darkness, that feels appropriate. Outside your room, the Earth continues moving. Even if you feel perfectly still, you are traveling around the planet's axis. The planet is orbiting the Sun. The Sun is moving through the Milky Way. The Milky Way is moving through a universe filled with hundreds of billions of other galaxies. Somewhere in those galaxies, stars are being born. Others are dying. Black holes are quietly bending spacetime. Photons that began their journeys billions of years ago are crossing the darkness. And everywhere, at scales too small for your senses to perceive, quantum systems are interacting. Particles meet. States evolve. Entanglement forms. Decoherence spreads information into the environment. The quantum universe continues doing what it has always done. It does not wait for you to understand it. And perhaps there is something peaceful in that thought. You are part of a reality far deeper than your senses reveal. The solid world around you is built from atoms that are mostly empty space. Those atoms obey quantum rules. The elements inside your body were forged in ancient stars. The space surrounding those stars may itself emerge from structures physicists are only beginning to understand. And somehow, from all of that complexity, you are here, able to wonder about it. Perhaps that is the strangest thing of all. The universe has existed for billions of years. For most of that time, as far as you know, there was no one here on Earth asking what any of it meant. Then stars formed. Planets gathered. Chemistry became biology. Life became complex. And eventually, one small part of the universe became capable of looking back at the rest. Capable of building laboratories, writing equations, splitting atoms, entangling particles, and asking why reality is the way it is. You are made from the same universe you are trying to understand. In a very literal sense, the universe is investigating itself through you. So perhaps the terrifying truth about quantum entanglement is not terrifying at all. Perhaps it is simply humbling. Reality is stranger than your intuition. Distance may not mean exactly what you thought it meant. Separate objects may share relationships that cannot be explained by local hidden instructions. And spacetime itself may eventually turn out to be only one layer of a much deeper structure. But you do not need to understand that structure tonight. You can simply know that the mystery is there, waiting, quietly, beneath everything. And as your thoughts begin to drift, you can return one final time to those two particles. Imagine them moving apart through the darkness, farther and farther, past planets, past stars, across distances too enormous to picture. They do not speak. They do not send messages. Nothing visible passes between them. And yet the correlations remain. A quiet reminder that the universe is not always divided in the ways it appears to be. Perhaps one day humanity will understand exactly what that means. But for tonight, you can simply let the question drift away with you, into the darkness, into the silence, and into whatever mysteries the universe is still waiting for you to discover.